One is up late, and the other one is ending their day. So we're going to travel around the planet this morning, which befits an Earth system modeling workshop. So two talks before the coffee break. Both of them are going to be virtual. Our presenters are online. So again, when the speakers are done, obviously you will have to go to the mics for questions. Otherwise, they won't be able to hear you. And that way also they can see you because we can focus the camera on that. So the first talk is by Zhenya Song. So we'll pop up his presentation and you can take it away. And I'll try to hold up the sign with about 15 minutes to go.
Okay, thank you. Thank you. Thank you, the chairman, for introduce my presentation. Actually, good morning, everyone. In fact, it's 11 p.m. here. You know, it's midnight in China. Unfortunately, I cannot be on site for face-to-face discussion due to the travel policy. It's my honor to give a talk in the workshop on modeling the climate system and at ultra high resolution. I'm Zheng Yasong from the First Institute of Oceanography, Ministry of Natural Resources of China. In fact, my institute belonged to the State of Oceanic Administration, be like the NOVA. Okay, in 2018, our headquarters was merged to MAR. All things doesn't change except the headquarters. Okay, so before I start the talk, I would like to introduce myself. My undergraduate degree is in applied mathematics, and I have worked on climate model since 2003 when I was studying for my master's degree. In the past 19 years, I have developed the FLESM version 1 and version 2. And recently, I started to working on applying machine learning to model development and application. The main content of the talk today is to introduce the key issue of climate modeling development through the the history of our FLESM, one of the Earth system model. Okay. My presentation consists of following 4 parts. The first is the background. The topic of this workshop is about the ultra high resolution. So I'd like to start from the talk for the model resolution. As we know, ocean models have become increasingly important for understanding oceanic dynamics processes and ocean environment forecasting. Improving resolution is one of the best ways to resolve the small-scale process, such like the submeso scale, and other phenomena, and then improve the simulation, forecast, and prediction ability. Okay, from the left figure, we can see that the ocean model have been developed with finer resolution from 5 degrees to about 2 kilometers due to the increase in the computing power. And from the right figure, the result also shows the model with a finer resolution has a better simulated performance, especially on the small scale structure. However, there are still bias in the high-resolution model. For example, this year, Dean and other authors from IAP and NCAR found that the ideally sovereign ocean model trained to simulate the large mesoscale energy intensity in the edge-rich region, while small mesoscale energy intensity in the ID per region. For the climate model, as we know, the resolution of CMAP6 models are also fine, but as shown in the right figure, it seems that the SLT and SSS bias still exist and do not be reduced too much. These results indicate, besides improving resolution, suitable parameter scheme is also important. Therefore, recently, the development idea of our model is mainly on the parameter scheme as well as improving the model resolution. More specifically, our research focuses on the role of ocean surface view, while small scale process in the ocean and the climate system. Actually, during past 30 years, we have developed a series model, including the Maximum Wave model, FLCOM, FLESM, and FLAW. All of these models are coupled with ocean surface view. So I will introduce one by one briefly. So besides the Maximum Wave model, the FLCOM is the ocean wave tide coupled model. Compared with other ocean models, the simulated ability is dramatically improved in the upper ocean by considering the wave-induced mixing. Based on the FLCOM, we also published our forecasting system with 10 kilometer resolution through WCRP official website and apps. Now we are developing the new model with about 4 kilometer resolution. And the FLAW is the regional atmosphere ocean wave coupled model. By considering the BV, the mixing wave, the wave induced mixing and the sea spray effects, the simulated strong typhoon intense bias has been reduced by 22%, and super typhoon intense bias can be reduced more than 15%. It should be noted that the weak typhoon intense bias is not reduced too much. And for the climate model, we developed two generation FLESM coupled with wave model. Besides the effect of wave-induced mixing for ocean, the wave-induced sea spray on LC heat flux, we also incorporated the effect of surface wave, like the stock strips on LC moments and heat flux, and also include the effect of the SLT Daniel cycle on LC sensible heat flux. All of our work indicates that the ocean surface wave have an important role in the upper layer of the ocean and the LC exchange and should be paid more attention. Following, I will introduce the history of FLESM and then give the perspective on the ESM development. So next, I will first introduce the development idea and the result of FLESM version 1. The figure shows the derivation of SLT, which is influenced by many factors. So we focus on the SLT bias in the upper ocean firstly. It's a multi-modal mean lunar average ocean temperature bias from the IPCC TAR report. We found that the ESM in the subsurface generally have a cold bias, and in mid-latitude, the mixed layer simulation is shallow. Why? We notice that the standalone ocean model also face similar bias, such as shallow mixed depths. The low panel are from observation, and the up panel are from the standalone ocean model. We can see in the subsurface that the temperature is colder in the model than in the observation. It's very similar to the results from the ESM. So It's a common problem for all standalone ocean models. Therefore, we think some important processes are missed in the ocean model. Cold temperature bias in the subsurface and shallow mixed layer depth means surface energy cannot be transferred into the sublayer, which indicates that the vertical mixing is insufficient. So there are also many studies have suggested that the wave breaks to produce mixing. However, vertical mixing from wave breaking is most limited to the top few meters and is too weak. Therefore, previous studies did not consider wave mixing in the ocean model. In 2004, our group found that the non-breaking wave also can generate vertical mixing and deduce a mathematical representation. So we can also calculate the non-breaking wave induced vertical mixing, aka BV, according to the wave parameter. Here shows the spatial and the vertical distribution of the BV. From the distribution of the 20 meters average BV, we can see that the BV is very large in the middle latitude due to the large wave height. More important is that, in fact, the depth of BV can reach to 100 meters. So we incorporated the BV into the POM, one of the standalone ocean model. The low panel are from observation, and the middle panel are from the alternate POM without BV, and the upper panel are from the result with BV. It can be seen that the simulated up temperature structure is much improved in the POM with BV. It indicates that the BV can be used for improving the ocean model simulation ability, especially on the upper layer. So we also test the BV in other ocean models such as MOM, POM, NEMO, ROMS, and FASON. All results suggest that BV can reduce the bias in the upper ocean. So it also indicates that the BV is one of the important missing parts for the upper ocean simulation. So meanwhile, as it's a new theory, we verified it through laboratory experiment and field observation. So we know now we know the BV can reduce the cold bias in the upper ocean in the standalone ocean model. So we think it should also play an important role in the ESM. Therefore, we incorporate the BV into the ESM first. We found that BV does improve the simulation capability of the upper layer of the ESM. The temperature evolution of up 400 meters in the south and the north hemisphere average over many years is given here, and we extend this figure represents the two years. So the black line is the observation, and the blue line is the result of the alternate model, and the red line is the result of considering BV. It can be seen that the upper layer temperature is closer to the observation after considering BV. Also, we found that the SIT simulation capability has also improved because the simulation bias of the upper ocean temperature becomes smaller. Moreover, we have tested several models, including Chinese model FGCM from IAP and the BCCM from Beijing Climate Center, and also CCSM3 from NCA USA. The numerical results suggested that all of them can improve the simulation capability. Subsequently, we present the mechanism of the BV effect on the tropical SIT in the climate system after in-depth analysis. So based on the above work, we construct the FL ESM version 1. I think it's the first ESM including ocean surface wave model. This framework of version 1 considers the atmosphere, land surface, sea ice, ocean, and ocean surface wave model. The wave model receives that the 10 meters of wind from the coupler, and then calculate the BV and then send it to the coupler. The ocean model receives the BV and other forcing data from the coupler. As it's an Earth system model, we also include the carbon cycle process. It's another story. I'm not to talk about too much of the carbon cycle here. So FLESM version 1 participated in the CMAP5, and FLESM, I think, is the only ESM coupled with the ocean wave model. Compared with our CMAP5 model, the global mean SIT simulated ability is very well. Here is the global annual mean SIT evolution from 1815 to 2005. The thick black line is the observation, and the thick blue line is the FLESM results. It's very close to the observation. We calculate the global mean bias, and the rank of FLESM is 8. Here is the mixed layer depth of the South Ocean. The rank of FLESM is 6, which indicates the FLESM has a great simulated ability in the upper ocean. In the global mean scale, FLESM version 1 showed a good performance. However, we noticed that if we focus on spatial bias of SST, we found there are still facing large bias, especially in tropical region. Due to the climatology SST bias over the tropical Pacific, FLESM version 1 also suffering from similar common problem to other CMAP5 models, such as a regular period of roughly 3 years and spurious phase locking for the ENSO bias. So how to improve the simulated ability further? We noticed SIT is a variable at the LC interface and is influenced not only by the ocean, but also by the atmosphere, as well as the LC flux. The previous study showed that the oceanic process are improved by considering BV. So we next continue to improve the ESM from the view of the LC flux. Therefore, we move to the LC interaction for developing the version 2. Based on this idea, we developed the FLESM version 2. In addition to the non-breaking surface wave-induced mixing, which has been included in the FLESM version 1, there are 3 more physical processes in version 2, including the effect of surface wave shock drift on LC moment and heat flux, the effect of wave-induced sea spray on LC heat flux, and the effect of SIT Daniel cycle on LC heat and heat flux. I'll introduce these three processes one by one briefly. First is the shock drift. As you know, during the wave motion, water particles always are not quite close. So the surface drift is the Lagrange average flux velocity induced by surface wave motion. In other words, it's the net mass transport. The velocity of surface drift can be more than 10% per 10 centimeters per second in the westerly belt of the South Ocean. As part of surface water movement, the surface drift is more than 10% of the current velocity in most of surface ocean, and it could be more than 60% in some region of Pacific, Atlantic, and South Ocean. More importantly, we notice the direction of South River is different with the ocean surface current in most regions. So during the calculating the LC flux, the velocity is used as the difference between the wind speed and the current ocean speed. In fact, at the LC interface, the surface wave induced surface drift are compared to the surface current velocity. They should be considered in the calculated the velocity difference. So we incorporate the surface drift in the LC flux calculation. Then based on the numerical impairment, we found that surface drift can reduce more than 30% cold bias over the North Pacific and Atlantic. The second process is the effect of sea spray on the latent and seasonable flux. Sea spray refers to the water droplet and aerosol particle that are released from the ocean to the atmosphere when ocean surface waves are breaking. And it not only depends on the surface atmosphere condition, but also on the ocean surface wave condition. The water droplets can exchange a seasonable heat with the air during this process. In the FLESM version 2, we consider the sea spray effect on the seasonable and latent flux, as introduced by Andreas proposed in 2015. We also calculated the light and seasonable heat flux and found that the ratio of heat flux induced by sea spray to total heat flux can reach more than 50%. It indicates that the effect of sea spray cannot be ignored. And also we ran the sensitive experiments. And based on the numerical experiments, we found that the sea spray can reduce more than 30% warm bias over the South Ocean. And the third process is the SIT Daniel cycle. SIT had a dramatic Daniel cycle due to the solar, the sun. The amplitude of the Daniel cycle variation in SIT can be more than 1 degree from the observation, and it is not negligible in the RC interaction. To consider the SIT Daniel cycle is very simple. Just increase the coupled frequency to 8 times per day. However, the amplitude is also important. Previous study revealed that the vertical resolution of ocean model should be 1 meter at the top of ocean to simulate the accurate amplitude of the SIT Daniel variation, which it is a great cost for the ocean climate model. Therefore, we develop a parameter scheme, which is a function of wind speed, shortwave radiation, and the first layer temperature of the ocean model. It can simulate a more accurate amplitude of SIT Daniel cycle without increasing the vertical resolution. So this is the numerical result for the SIT Daniel cycle. In fact, Based on the numerical impairments, we found that the SIT Daniel cycle can reduce the SIT bias almost the global, although the magnitude is not very large. Then, based on the above analysis, we developed a new generation of the FLESM, which is version 2. Compared with the version 1, we incorporated the 3 new physical process into the model, and also increased the spatial resolution and coupling frequency. So compared with the FLESM version 1, the simulated ability of the version 2 is much better. The SIT bias are reduced by more than 30%. In the tropical region, the improvement is more than half, I think. And due to the improved climatology SIT simulated ability in the tropical region, the version 2 also has a better performance for INSO. Not only the amplitude, but also the period and phase locking. Also the FLESM version 2 participated in the CMAP6 in 2020. Compared with other CMAP6 model, the global mean SIT simulated ability is improved further. Here is the global annual mean SIT evolution. The blue dot is the result of the version 2. It can be seen that the version 2 shows great performance in the global SIT. The integrated rank of FLESM version 2, including the mean error, STD error, correlation, MSE, and the long-term trend error, is 2 among the 48 CMAP6 models. And last year, Dr. Lee from PCMDI of USA evaluated the INSO simulated ability of 59 CMAP6 model. And we found that FLESM is the #1 for the integrated index of symmetry, amplitude, duration, seasonality, and diversity among the 58 CMAP6 model. And FLESM version 2 also has a good extreme event simulated ability. Marine heat waves are extreme climate events that last for days to months. And it's very important. We evaluated the marine heat waves result from 29 CMAP6 model and found FLESM had more skill in capturing the feather of the motion wave. So also the dynamic downscaling is useful for regional climate simulation and prediction. The background and the boundary conditions are from the global ESM. Therefore, the global ESM simulated ability is a key factor for downscaling. This year, Dr. Zhang from Nanjing University evaluated the simulated ability of CMAP6 models for downscaling over 14 key domains. They claim that among 37 CMAP6 models, the MPI ESM and FLESM2 rank top 2 due to their overall good performance across all domains. Okay, that's all about the FLESM development. So next, I'll talk about some ideas for future model development. The results for FLESM indicate that the physical process improvement is very important for model development. From the view of ocean surface wave effect, especially on the high resolution, there is more work we can do. We found that the parameter scheme used in coarser resolution may not work in the high-resolution model. We should reconsider the parameter scheme with high resolution. In the following, I'll give two examples. The first is albedo. As you know, in the ESM, the ocean surface albedo is usually set as a constant, such as 0.055. Recently, we found that albedo can range from 0.02 to 0.2 and can be represented as a function of this angle, wind speed, water vapor pressure, and wave height. We tested the new albedo parameter scheme and found that the results are almost the same compared with the constant scheme when ocean coupling frequency is once per day. But when we increase the coupling frequency, such as 6 or 8 times per day, the wave effects on the albedo become more important. And the second is wind stress. In the earlier study or in the application of the model, there was an assumption that the wind stress was generated by the wind and the wind stress was aligned with the wind direction. What does it mean? It means the direction is same between the wind and wind stress. Recently, our observation showed that the wind stress deviates from the wind direction. In special cases, it can be 180 degrees. So that means the wind stress is opposite the direction of the wind. But certainly, our new finding is based on the observation data with second interval. So if we average the observational data to hourly interval, the difference is not so much. So it suggests that the previous wind stress parameter scheme is not incorrect, but not suitable for high resolution. For the higher resolution with small time steps, we should improve the wind stress parameter scheme by consider the wave effects. So the above are the idea for the parameter scheme for ultra-high resolution model. Following, I will introduce the view of new technology, such as machine learning. As we know, AI is popular and showed the good potential application to the modeling and forecasting. Here, I'll introduce several thoughts on integrating machine learning and modeling. Machine learning, I think we include the shadow and deep learning can be assumed to be a static learning method. Therefore, we propose 6 basic approaches to integrating machine learning and the ESM. These approaches are new. These 6 approaches are new: statistical forecasting, physical mechanism detective, parameter optimization, model results correction, submodel replacement, and numerical model solidity. The details can be read in my paper published in Clever Exchange last year. Here, I only take 2 examples in the following. So first is the model results correction. The black line in the figure is the observation, and the blue line is the model results from FIESM version 2. Okay, it's from version 1. Sorry. We can see that we can see that FIESM still has a bias, which increase the future prediction uncertainty. Therefore, it is impacted to improve the model predictability by finding the historical simulation derivation pattern and correcting the derivation of future prediction. How can we reasonable correct the derivation? We analyzed the data and found that the bias was different due to the existence of signal with different time scale. Therefore, we first decompose the data using the EMD method. Non-IMF components were created by performance EMD on the observed and simulated SAT data. Then six new time signals were combined as a seasonal, annual, interannual, decadal, interdecadal, and over 80 years scale. Based on this, we use a 3-layer BP natural network to correct the signal of these 6 different time scales. After correction, we then combine them into complete data. The results showed that the revised model effectively reduced the derivation in the global monthly average SAT simulated by the model. The MSE was reduced by 76% from 0.6 to 0.09 degree. And the mean absolute derivation also was reduced very much. The correlation coefficient from the observation was increased from 0.3 to 0.9. So the same
about 5 more
correction
minutes.
model.
Sorry, about
Okay,
5 more
okay,
minutes.
thank you. No problem. So the same correction model was then used in correct the future global average SAT and the 3 emission scenarios. We found that the ESM may overestimate global warming in the future. Our conclusion based on the model correction method may not be correct, but it provides a possible answer. Okay. So the second is fast forecasting for wave height. Ocean surface waves are composed of local wind wave and swell propagating from other sea area. So the wave model can simulate the wind, the wave, and swell with high accuracy, but the calculation amount is very large. It's a 5-dimension problem. Traditional statistical method calculates fast, but cannot give the correct information of swell. So we developed the model named OSVU CN based on the convolution natural network. It can finish 7 days forecasting only in seconds, although the accuracy is only 19% to wave model, but it is very useful. As we know, the component cost will be almost 3 orders if the horizontal resolution is fined by 1 order. In other words, if we improve the resolution from 10 kilometers to 1 kilometer, the computation cost will be 1,000 times. The new technology like the AI provides a possible solution for fasting model simulation and also can save the energy. Okay, the above are all of my talks. Model development especially for ultra high resolution is not easy. There's a long way to the predict the ocean. Here, I only list the potential research we should pay more attention to. The ocean surface view is one of small scale motion. So when we are prepared for ultra high resolution model to predict the ocean, it is in uh, it is inevitable to take into account ocean surface waves. I believe the ocean surface wave will play more and more important role in ultra-high resolution modeling. Okay, I stop here. Thank you for your listening. And it's a pity that I cannot be there for face-to-face discussing in detail. I hope the COVID-19 pandemic can be ended and see you as soon as possible. Okay, thank you again.
Thank you very much. Does anybody have questions? If you do have questions, please go to the mic. I'll actually start with a question. When you put in the correction, the neural network for SSTs, are you doing that in a coupled model? And if so, what do you do about the energy? How do you conserve energy when you do that?
So do you mean this work?
Yes. So you correct the SSTs, but doesn't that change the energy in the system?
It's just correct the SLT. It did not consider the energy and other, only for the SLT bias correction.
Okay.
Only for this only one variable.
Okay. Any other questions? Okay, well, thank you very much. We appreciate your staying up late. Hopefully you can get some rest.
Okay, thank you.
Have a good night.
Okay, thank you. Have a great day.
Okay, next up, we're holding up Xenia's bedtime. Now we're holding up Martin's dinner. So Martin Losch will talk about sea ice, and I believe he is also online. Great, we can see your presentation.
Okay, now you should be able to hear me.
Yes, we can. Go ahead.
All right, great. Okay, thank you very much for giving me the opportunity to present my research here. In fact, I should start by acknowledging my co-authors. Most of the stuff that I'm showing today was really done by my recent PhD students, Niels Hutter and Damian Ringeisen, here at the Verwegeneitsinstitut in Bremerhaven in Germany. But a lot of the work would not have been possible without interaction with Bruno Tremblay and his PhD students, Mathieu Plante and Amélie Bouchard. So I'll start by showing, let's see if I can, by showing a time-lapse video, a movie of sea ice. And in the past, I would ask the audience whether they could tell me which satellite would have taken these images. But I've shown this so often, I think others have too, that I will give this away immediately. This is, of course, not a satellite. And since this is a modeling workshop, this is the result of a model that was run, the MIT TCM that was run by Dimitris and Chris Hill, whom I believe is in the audience. But I'm showing this to illustrate how far we have come with our current sea ice models, but still we need to ask the question, which is the title of this talk, is when we model sea ice at the flow size scale, and you immediately see there are individual flows being resolved, is the current modeling approach still useful or viable, and do we need more valid, and do we need more new modeling approaches? I also show this because this illustrates that sea ice is a very heterogeneous mix of ice flows of all sizes that forms a thin insulating sheet between the ocean and the atmosphere in the polar regions. The volume of the sea ice is very small compared to the volume of the ocean or the atmosphere, but it is important because it inhibits fluxes of heat and properties between the atmosphere and the ocean, and being an important player in this climate system. So in the past, this complex system has been modeled in numerical sea ice models by treating the system as a quasi-continuous or a quasi-continuous non-Newtonian fluid to describe the dynamics, and I will quickly go into this non-Newtonian dynamics, and in particular the viscous plastic rheology, which has been the workhorse of present-day climate models. And but this assumption, or especially the continuity assumption, starts to really break down at high resolution when we start to resolve individual flows and cracks in the ice. The other question that I'm going to address a little bit is how to evaluate these highly heterogeneous fields that you've just seen, and also what we can learn from these flow resolving simulations that are done with the old-fashioned viscous plastic rheology. At the end, I'll very quickly touch upon alternatives and a little bit of thermodynamics, but this is mainly going to be to talk about the dynamics of sea ice. I hope that's not disappointing to you. Okay, so this is my only slide with lots of formula. What I'm doing here, I'm wondering, can you see my pointer as I point at something here? I should be pointing at the. I'm not hearing anything.
Yes, we can.
Okay, good, great, excellent. So sea ice has a very small volume, and the lateral extent is a lot larger than the vertical extent. So we can treat it as two-dimensional. So we're talking about vertically integrated equations here with the momentum acceleration on the left-hand side and the stress divergence term here, plus the rest. And the rest is basically Coriolis and the stress at the surface and the bottom of the ice and some down gradient geopotential term. So this looks relatively similar to shallow water equations, but it has the stress tensor is actually more complicated. So in a primitive equation model, the stress tensor would be linear friction law of a coefficient times the gradient of u minus the pressure, so that this would be the pressure gradient term plus viscosity in the end. But in a viscous plastic rheology, this stress tensor has a more or less complicated relationship with the so-called strain rates, and the strain rates are the velocities differentiated with respect to the spatial directions. So when you stick the definition of sigma into the momentum equations, you end up with terms that look like the one at the bottom here in the bottom red rectangle, and so you have these viscosity-like terms that have coefficients that depend on the ice strength P and on this delta. And delta again is a complicated function of the strain rates, and this can become very, very small or very, very large within time steps and grids and grids. So it's going to be, it's very heterogeneous and very highly fluctuating. This makes makes these equations extremely difficult to solve. But once you solve these equations accurately, the stress states all lie within what we call a yield curve, and here I have a just as a logo and as a pictogram. So the yield curve of, let's just look at the blue ellipse here. The yield curve and that defines when the ice starts to move or deform plastically. So basically, solving the equation exactly puts all the stress states on the blue curve, and there are no states outside the curve, and inside the curve we actually find the so-called viscous states that emerge when we regularize this delta for very, very small numbers. But the regularization is so weak that most of the time sea ice models are in plastic or deform plastically, and this is what you've just seen in this animation. So maybe enough of what really VP is, but there are issues with these continuum models, especially at the high resolution. So first of all, if we really want these equations to converge, they're super expensive, and even if we are ready to or if we are willing to spend a lot of computer power at high resolution, it becomes very difficult to actually make these systems converge. There are a couple of attempts. I listed a few here, especially the last one by Xi et al. Seems to be promising, but I would call this problem unsolved. There are systems, for example, the ones that are described in Kimretz et al., and which is being used in FESOM, which you heard about yesterday, where the EVP solver is being regularized so that the solutions that come out are at least smooth, but they're still going to be quite expensive if you really want to have converged solutions. Another problem is that these traditional models have no tensile strength. That is a kind of a side problem. It can be fixed if necessary, and there are examples of do this. But one of the assumptions about the sea ice models, apart from the continuum, is that the dynamics are assumed to be isotropic, because in these large boxes that people thought of in the 70s when they started modeling this, there were enough leads present so that we can not really distinguish a direction. But this, of course, changes as the resolution increases, and you are suddenly looking down an individual lead or along the edge of a certain ice flow. The main problem remains is the continuum assumption still valid at high resolution. So why do we still use these models? Because we have years of experience. We know how they work. We know what they can and what they can't do. They are relatively cheap if you sacrifice the conversion constraint that I just talked about. So they're in a climate model, I assume that you don't want the sea ice solver to use up 90% of their computer time. So they are usually tuned in such a way that they're not very accurate, but cheap. And then we can transfer our experience from continuum, ocean, and atmosphere models, for example, advection schemes, to the sea ice model. And they're fairly straightforward to couple to the atmosphere and the ocean. At least the spatial problem is more or less straightforward. Okay, so another look at sea ice, at the simulation. This is the same simulation that I showed in the beginning. This is a 1/48th degree simulation with the MIT GCM, and it's an ocean sea ice simulation that was carried out by Dimitris Menemendes and Chris Hill in I don't even know, in 2014 or so. And I think this is one of the first K-scale ocean simulations. The resolution, the grid spacing in the Arctic, which we see here, is on the order of 1 kilometer and less. So when this animation was made by Niels Hutter, and when you let this run, you see that there's lots of structure in the ice cover here. What we see here is mostly thickness. Dark means thin, and white means thick. There are these long features here that are called linear kinematic features, or LKFs. That's what we are interested in, and because these can be observed from space. Yeah. So again, you can see that this continuum assumption is kind of weird when you resolve these individual flows, and then also the isotropy is not really there. The simulations are clearly anisotropic, and this anisotropy emerges naturally from the simulations. So this looks nice. This looks like something that one would also see in a satellite, maybe. if one doesn't look very closely, but is it realistic? And it's now going to be interesting to see what metrics we can use, because similar to an ocean model where that has a lot of eddies in it, it will not be possible to put these linear kinematic features at the right position unless you use some fancy data assimilation scheme. So we have to, I mean, we can look at the large scale distribution of ice thickness and concentration and drift as we did with coarse resolution models, but we also need to do something about the statistics. And there are two methods that I would like to show you here, and this is not new, but that's what we typically do to evaluate our models. And one is a scaling analysis, and the other one is a feature-based analysis that for which Niels has developed a lead detection and tracking algorithm based on work by Stefan Lino and Wolfgang Dierking. So but first, let's go to the scaling analysis. If for the scaling analysis, the following observation is important. So here are three images of the sea ice in the Arctic, and if this grid wasn't there, and if I didn't put the length scales at the bottom of these satellite images, then it would be very difficult to tell what the length scales of these features are. So the observation is that that sea ice is somewhat self-similar. That means the smaller you go, the smaller the features or the structure is. This is also called fractality, right? There's a certain fractality to this, and we know from based on this, the group by Jérôme Weiss has shown that these satellite images, the total deformation, so that's like a norm of the strain rate tensor. So the total deformation scales with both the length scale and the time scales. And these scaling laws or properties have been used to compare, the fractality or the similarity of sea ice deformation between observations and model simulations. And here's a long list of papers where this has been done. And there's also a second, a little more difficult power law scaling, where even the higher moments of total deformation scale with the length scale, but there's also a certain quadratic structure function that one needs to reduce in order to be comparable to data. So this is kind of a statistical approach to checking the intermittency in the localization, where when this is met properly, that means that large deformation events are more localized and also more intermittent than no deformation events. This has been discussed in Rampal et al., for example. Okay, just as an example, I start with the result of the paper that tried to say that the VP models are no longer sufficient for our simulations. Here you see in this plot the spatial scale on the x-axis and the mean total deformation rate as a function of spatial scale on the y-axis. And the green crosses are results from a satellite product, RGPS. This is the radar-sat geophysical processing system by Ron Clark, and which is basically drift velocity, and then from that you can derive deformation. And the squares, the blue squares, is the VP model that that in this paper Girard et al. In 2011 used, and you see that that while there's a slope of a certain there's a constant slope for the data, the model basically has no real scaling, and this basically led the group of the authors here to conclude that the VP model is not sufficiently localized compared to the RGPS observations, and that one needs a new modeling approach, and this would be this elastic brittle approach that you may have heard of, and I will talk about this a little later. But they show in their paper that there is a scaling which is not quite the same as the observations, but at least there is some scaling. So oh yeah, and what I forgot to say is that the numerical models that they used had a grid spacing of about 10 kilometers, whereas the resolution of the data was about 12 kilometers. So Niels Hutter then showed that for models with a much higher resolution, so with 2-kilometer grid spacing, this conclusion is no longer valid. So in the middle pane, you see the same as in the left, except that now we have in orange the data, and in green and blue 2 different model versions of the MIT GCM, and the 3 different groups of lines are the first, second, and third moment. And you see in all cases there actually is a scaling, and what even more so, the scaling also follows this quadratic structure function. And there, I mean, so from this we can conclude that the deformation is very well localized if the resolution in the VP model is high enough, and that the stronger deformations event are more localized, which is exactly what we want to see. And also, what's just maybe even more interesting is that these different models give different results, and so that means there is some room for tuning. These 2 models differ only in the way they treat the subgrid scale thickness distribution. Otherwise, they are identical. Okay, so but bottom line, from the scaling analysis alone, we cannot reject the viscous plastic model as we use it today. We just need to crank up the horizontal resolution, and I think at this workshop this is exactly what is the plan. So we can still use it from this point of view, or based on the scaling analysis. And the second type of analysis is this feature-based analysis, where when you look at look at a image of this RGPS total deformation. I'm not sure if you can recognize it's the Western Arctic with the Canadian coast here and the Russian coast up here, and this should be Alaska, so there's only data for the West Arctic available. So this detection algorithm uses gradient information here in this plot to extract these structures and filters them and forms a skeleton, and then segments, divides all the different pieces and into different segments of LKFs and reconnects these LKFs. So I should have said that these lines here are lines of large deformation, and these are then usually associated with LKFs. So these linear kinematic features, which are either leads, so openings, or ridges, which cannot be decided from this plot, but you would need to look at the divergence and the shear individually. Okay. Anyway, you can then, after dividing all these different segments, the lines into different pieces and segments, you can reconnect them based on certain assumptions. You know, are they oriented along a single line, and what is the strength, etc. So that there are certain criteria to do that, and this results in a list of LKF objects. And on top of this, Niels came up with a tracking algorithm where he advects these objects with the observed drift from the same data set, and then after this drift step matches the objects with objects from the next image, so you not only do you have a list of objects, but you also have a temporal evolution. This data set is available, and if you want to try it yourself, there's even a Python package that does this for you. So once you have these objects, you can now do all sorts of statistics, not just scaling. And one of the obvious things to do is look at the relative frequency of LKS, which is shown on the left. And here there is some similarity between between the data at the top and the model at the bottom, especially, for example, here in this area of the Russian coast or the Russian shelf. This seems to be a hotspot of LKF formation. The same here in Wrangel Island, and this you can see something very similar in the models. That apparently there's also lots of LKF stuff going on near the coasts, which is not resolved by the RGPS data. Same here at this group of islands, which the RGPS data doesn't cover. But then you can also look at other things like lifetime of LKFs, and there even is a scaling for that. So depending on the model, there is actually quite good agreement between observations and model results. But one based on this, one could maybe reject the green model, but there are other places where the green model works better than the blue model. But what all models and not only the models that we look at here in this plot, but also in a large comparison study with many different high resolution models. All models have an issue with the intersection angle. So that's the angle between two LKFs, or the two LKFs that form at the same time. And the observations tell us that there's a preferred angle around 40 degrees, and the models all get this wrong and have a preferred angle around 90 degrees. And this is actually independent of the type of grid here. You could imagine that it's the specific rectangular grid that does this, but even FESOM with this triangular grid has the same issue. So there's something wrong, and we can maybe look at this with even higher resolution simulations. So these are now simulations that that Damien Bringeisen carried out for his PhD, and these are simple or idealized compression experiments where you have a solid wall at the bottom here of this plot, and some force being exerted. The ice breaks and moves and slides along these fracture lines, where the shear deformation is largest, so in the beginning of the simulation, the shear deformation starts to look like this. Incidentally, this is independent of resolution. We use here delta x of 100 meters, where the continuum assumption definitely breaks down. And what Damien found is that even from geometrical considerations, found that there is a lower limit for this fracture angle, which is half of the intersection angle. So we would expect something on the order of 20 to 25, but in the end we get there's not possible to get this, to make this model create fracture angles below 30 degrees. And this is something that we actually learned now from geometric consideration, but only after having looked at these type of simulations for a long time. And Damien comes even up with a solution for this by changing one of the assumptions of the viscous plastic model, that is the so-called normal flow rule that defines the way the ice moves after fracture. And he introduced a second ellipse, which has a different width. And with tuning the second ellipse, and I'm not going to go into detail here, we can actually change the behavior of this model in this idealized situation to produce smaller and smaller fracture angles with a flatter and flatter plastic potential ellipse. Which would be the red ellipse in this plot. So this is just to show that there are benefits from running these models at high resolution that go beyond the pure climate. It's just we learn about the system and so on. Okay, then I think I have 5 more minutes, and I quickly want to go into the alternative methods that are around. So the most prominent one is probably the brittle rheologies, and most notably this Maxwell-Luster brittle rheology, where the expression for the stress, just as a function of the strain rates, is augmented by some elastic term. This now allows elastic waves in in the system. But more importantly, this brittle rheology introduces a new variable that's called damage. That is basically the history of deformation, of breaking. And this is and this is done in a way that the more a certain failure law is being violated by the wind-induced motion, the larger the damage is, and this has then an impact on the next time step. This type of rheology has not been implemented in any large-scale models so far. The ones that I know of is this McGill sea ice model by Mathieu Plante and Bruno Tremblay, which is a standalone sea ice model mostly used for tests. We are currently in the process of doing this and in the master thesis of Miriam Bourget in the MIT GCM, and it looks quite nice, but we're not quite there yet. And but the most prominent example, of course, is this NextSim, which is a fully blown sea ice model but also with a very, very different type of grid, a Lagrangian grid, in the group by Pierre Rambal in Bergen and Grenoble. They initially started to use this MBB, Maxwell-Laster brittle rheology, and now they have something new they call brittle Bingham-Maxwell rheology. But what's common to all of these is they still use this continuum approach. So we're not sure whether it's really allowed from a physical point of view. Or, from my experience with Miriam here, there are a couple of open questions that I think are important. So we don't know yet really how to really solve this properly, and the computational cost is probably not very low either, right? And then there are stability issues, and there needs to be some sort of coupling to the thermodynamics in order to heal the damage that is being created. Otherwise, your ice would damage very quickly. And there are ideas. Obviously, the next model has something developed for this, but the community doesn't have any experience with this. So I think this is still something that needs research. The other direction are discrete element models, where you go away from the continuity assumption and you have individual flows, like here in this animation by Rabatel from 2015, and I'm listing a few other publications that deal with these types of models. This is definitely super interesting, but in the context of climate models, I think there are many problems that still need to be addressed or solved. And I don't know about the computational cost; it can't be cheap. Okay, and finally, just two slides about thermodynamics, just because they are part of the system. But this sketch that I stole from a presentation by Perovich summarizes the thermodynamics. Basically, these are just the fluxes between atmosphere and ocean and ice, and solving the balance between these fluxes in some way leads them to melting and freezing of the ice. Of course, this is important for climate modeling to get these things right. But I think, or my point of view is that for high resolution models, this doesn't really cause a problem, because these models are typically 1D models with no lateral interaction, and at a 1 kilometer scale, I don't see how this should be changed. Subgrid scale processes are parameterized, for example, an ice thickness distribution. Again, I don't see how that should change with very high resolution. In a 1 by 1 kilometer box, you still have lots of different types of ice that justify having a nice thickness distribution. The only thing that I think is important to think about is this coupling, because the timescales of these models may require that the heat flux computations are not done within the ice model, but within the atmospheric model, because the atmospheric model can react so quickly to changes in the surface, and that may lead to not only physical but also numerical issues. And I know of at least 2 models that do it like this. So the old MPI ESM did this like this with ECAM, and the GEOS MIT GCM coupled system that Chris will talk about tomorrow, I think, does it also like this. Okay, but it's more that it's going to be interesting to have a high resolution model with thermodynamics, especially in the coupled context here. without an interactive atmosphere, we try to study the effect of these leads on ocean, on the heat flux that the ocean receives through the ice. And for this, again, Niels Futter dumped down a high-resolution simulation by smoothing the thickness fields during the simulation in order to suppress the lead formation, and then we compute the net heat flux through the entire Arctic ice cover, or the mean heat flux actually over 1 month. And here on the right you see a time series. This is not mature at all. It's just a teaser, and you see that the heat flux is on the order of 10 to 15 watts per square meter, and the blue curve is with leads, so the right-hand side plot, and the red dashed line is without leads. And you see there's a small difference, but the difference is really on the order of half a watt per square meter. But this is to say that the left-hand side model that is more or less like a coarse resolution model without leads still parameterizes the opening between the openings by the sea ice concentration, and which is again another subgrid scale parameterization of sea ice models that all sea ice models have. So it is not yet clear whether this extra information of the high resolution fundamentally changes the exchange of heat between ice, ocean, and atmosphere. But still, it would be interesting to look at this from an atmospheric point of view, because there has been a lot of work, and this is Christoph Lübkes and his group that looked at warm plumes over leads in the atmosphere and the dynamics. And if models start to resolve this in the atmosphere, it might still have a very interesting effect. Okay, this brings me to the last, or actually to my conclusions, which I put up here. So I think, coming back to the initial question, do we need to do new approaches, especially when it comes to coupling between ice, ocean, and atmosphere? And my opinion here is that the resolution is rather limited by the vertical extent of ice, so that when the horizontal scale becomes so small that we reach the thicknesses of 1 to 2 meters, then we have to take into account pitching, rolling, flexing of ice, and so on. Then we have to then we need to change things. But at the moment, at this kilometer scale, we are still fine, I think. Until we reach the super high scale, interesting dynamics emerge that are automatically anisotropic, and we can compare these results to data, and looks very nice in many circumstances, but not everything works. And the main problem that we have identified is that these fracture angles are too large in BP models. And why? Actually, I didn't say that, but why is this a problem? Because when you have a too large angle or a small angle, the density of LKS may change, and the number of leads and so on that are allowed in a certain area becomes smaller. So it is something to look out for, and maybe our different yield curves or different rheologies may help with this problem. We don't know yet. So, and the thermodynamic consequences of LKFs in coupled simulations promise to be an interesting area of research. And then I just showed you this heat flux stuff over leads, and with this, I'd like to close. Thank you.
Thank you very much, Martin. That was great. Any questions for Martin? If so, please make your way to the one of the microphones.
Yeah, hi, Martin. Thanks a lot for the great talk. It's Nikolai. So since we cannot really talk in Bremerhaven, I have to ask you here. So just to reiterate about the resolution. So you're basically saying that even going to 100-meter resolution is totally fine from your view. And another question is, do you think that including the more complicated thermodynamics like ice pack makes sense for coupled models of the kilometer scale, or that's really not something that we have to pay attention to right now.
So thanks, Nikolai. The first question, yes, I think we can actually go to very high resolution. I think the limiting factor is really the ratio between the vertical and the horizontal scale. At 5 meter grid spacing, I would become a bit uneasy about this. But up till then, the models seem to show the correct behavior, right? And it seems to even become even better. But again, at this one, I think we are safe at this 1 kilometer scale. And about the thermodynamics, I mean, the complicated thermodynamics like ice pack become very expensive because you have to advect all these super many traces that come with multiple layers and multiple ice thickness categories and so on. So one would have to think about that. But other than that, the thermodynamics of ice pack are so well advanced and so mature, I think, at this stage that yes, they should be used, unless you have very, very strong computational cost problems with this. But I think the more expensive part of the COS model will be the dynamics at very high resolution.
Thanks.
Hi, Martin. Thanks so much for your nice talk. Christian Jacob here from Monash Uni. I have absolutely no idea about CIs. I'm an atmospheric convection person. But seeing your results from this MIT GCM, I was wondering, is there some sort of program mechanism for comparing CIs models as we drive them to these very high resolution? Is there something your community has embarked on already? Is it something we should be doing and aren't doing? It's just sort of a more programmatic and organizational question, I guess.
So there was one effort that was sparked by one of the famous, so this is an Arctic community meetings. And in fact, oops, what did I do? Now I unshared my screen.
Yeah,
is
that's
that correct?
Fine. You unshared it. You can share it again.
Okay, but doesn't matter. I don't have to share it. So there's what is called CIREX, CI's rheology experiment, and this is exactly doing what you suggested. And this was organized by Amélie Bouchard and Niels Hutter, and consequently there are two papers called Bouchard et al. And Hutter et al. That came out this year. And there they basically collected a lot of different high resolution models and subjected them to these scaling analyses that I showed. I didn't show those results because they're not really mine, but also because they would be very confusing in a short talk. But in principle, we did all these, or they did all these comparisons and evaluate and discuss the results in terms of how resolution, how coupling, how there's even a coupled model in there, I think. And how grids and different types of grids and different types of solvers and different types of rheologies affect the solutions. And of course, this next model came out as one of the top runners, but the high resolution simulations of MIT GCM were also quite successful, and others worked on FESOM as well, right? So it's either you invest a lot of time. A lot of power in the high resolution of these CIS models, or you invest a lot of computer power in solving these more complicated rheologies like the next Maxwell-Astor-Brittle rheology.
Okay, and thinking ahead, since I still have the floor, thinking ahead, so this workshop is discussing, and seeing lots of efforts where coupled kilometer scale modeling, it's mostly round about the 5 kilometer scale at this point rather than the 1 or 2 kilometer scale, is taking off left, right, and center. And so I think it would be really nice to have a CI's evaluation effort almost continuously going, because this is just there's just gonna be more model runs, and I wonder whether we are ready for that. Sounds like we are.
Yeah. I mean, the VP models are mature enough to do this. I still have my reservations about the other types of models. I would be very much interested to include models that use these discrete elements And I think there's a group, I mean, the group in Los Alamos is developing something, but maybe I haven't looked closely enough, but I haven't seen any published results yet. And there are other efforts. So I would be very much interested in how these models can reproduce these statistics. So I agree with you. There should be some continuous effort in evaluating this.
And just being a
Especially
Southern Hemisphere person these days, even though I wasn't born there, I love this feature tracking because we're doing a lot of this in the atmosphere as well as convergence lines. And in fact, I'm going to look at how you do yours because there may be stuff to learn for us atmospheric guys. But has there anything been done to evaluate things around the Antarctic?
We haven't, I mean, in my group, we haven't done anything because typically the Arctic is more interesting because of the confinement by the continents, but the same type of features appear in the Antarctic, right? So especially in the Weddell Sea or so where you do have interaction with the coast. Or confinement by the coast, but since a lot of the stuff in the Antarctic is not really free drift, but close to free drift, all this rheology part, this non-Newtonian dynamics is not as important as in the Arctic. So that's why most studies focus on the Arctic. But I agree, we should also, I mean, this would be the next thing to do. Also have a look at the Antarctic. The simulations look very similar.
Cool, thank you.
In terms of structure. Mm-hmm.
So Martin, one last question. So you showed a bunch of models, sea ice models at sort of 1 kilometer and 2.5 kilometer, and they were at least coupled to an ocean and probably forced by an atmosphere. But if you're running in a coupled system, what resolution would you want to run at? And is there thought of actually running at a different resolution from the ocean to the atmosphere with the sea ice model, assuming the numerics of the coupling could be sorted out and the regridding could be sorted out?
Yeah. So I, to be honest, I have no experience with running a coupled ice-ocean atmosphere system, but I would argue that depending on the rheology that you want to use, so if you want to use these VP models, these viscous plastic models that I've been talking about mostly, we should really run them at least a grid spacing of 5 kilometers, if not higher. If we can, and even if the ocean is not running at this super high resolution, it's worth running the sea ice model because only then you get these structures. There seems to be some kind of threshold around 5 kilometer grid spacing. If you go to 10, then a lot of the structure totally disappears, and these models were designed for 20 to 100 kilometer grid spacing. So it's kind of weird. Right? There seems to be this gray zone between 25 and 10 kilometers where it's not quite clear what these models do. But at the higher resolution, it looks far more realistic than at 10 kilometers. So I would argue that. Or you go to something like NextSim, where you have damage included that then automatically introduces this heterogeneity to a larger degree. But this is a very different type of model, and I don't have enough experience with this to really confidently say anything about that.
Okay. Seeing no more questions, thanks. Lots of stuff to think about, lots of great observations and metrics to be used in new ways. So we really appreciate that, and have a good evening, I guess. Thanks for joining us.
Yeah, thank you very much. Thanks for giving me this opportunity.
Thank you.
Bye-bye.
Bye. Okay, so now we'll have a, right on time, look at that. We'll go to a coffee break for a half hour, then we'll come back with a series of talks before lunch. And then after morning. So ocean, ice, and now, certainly not least, Mike. And most importantly, land modeling. So thank you, Martin Best, for joining us.
Okay, thanks very much. I had a exchange with Jan Polscher over this, so we shared some ideas. So I've actually added Jan as a co-author on this. So at least there's some coordination between us on this presentation. Okay, so I want to start by just saying that over the last 50 years or so, there's been quite a lot of development in the land modeling. We've gone from a basic bucket model to something that's quite complex in terms of representing heterogeneity, in terms of its processes and things like that. But one of the things I notice here is it's all one-dimensional. We do heterogeneity, but it's all one-dimensional. So as we go to high resolution, surely we haven't got any issues. We're all just one-dimensional. Surely that's not, there's not going to be a problem, so anything to discuss. Well, hopefully over the next half an hour, I can show you that that's not quite the case. And I will apologise now that it's going to be a bit rushed, because actually there's quite a lot to get in with half an hour. And the other thing I'd say is I've only looked at the energy and water cycle. I haven't even considered the carbon cycle in this presentation. So there's even more to think about than I'm going to present. Okay, so let's start then and think about where some of the issues might be. Well, to start off with, the way we represent the heterogeneity. When we're talking about coarse modelling, the heterogeneity scales are actually quite big. So if you look on the left-hand side here, we're talking about an area of woodlands, maybe some area of pasture, some crops, and we represent that with tile schemes. So these are schemes where each individual surface interacts with the atmosphere, and there's no interaction between the surfaces within a time step. But as we go to high resolution, the scale of the heterogeneity changes. And if you look at those pictures on the right-hand side, you're looking at, say, sparse cover, where you've got some trees and you can see some bare soil, or maybe you see some snow between the trees, or even going to things like fruit crops and fruit trees, where you've actually got lines of trees with soil in between. So this tile approach isn't appropriate anymore. And what we then need to be thinking about is going to what I would say multiple source schemes. I mean, traditionally we've done things like dual source, but I think even more source than that, could be multiple source schemes. Now this isn't new. We've had land models that go back to the 80s that do this, but they're not coded up in our models at the moment. We've coded up the tile schemes. So to go to high resolution, we have to recode our models to be able to deal with these different scales of heterogeneity. That's one issue. That's the least problematic issue. Think about the next issue. If we think about within a grid box, and we've got some heterogeneity, over each of those surfaces, you have a growth of an internal boundary layer. Now, so the picture on the right shows you sort of a schematic of those growth of those internal boundary layers. And at some height, it all merges together, and you can't really see what's happening at any particular one surface. And that's called the blending height. So it is the height at which you no longer see a profile to an individual surface. Now, when we do this in the models, we use the first atmospheric level. So when we go to high vertical resolution, we're talking about order of 10 meters, maybe even lower for the first atmospheric level. That is well below the blending height, particularly in a convective boundary layer, where you're looking at least 20 to 50 meters. So this means that the theories we've got for doing surface exchange are no longer valid. Now, we're running models with these high resolutions at the moment, and quite frankly, we're getting away with it. And I can't wait I keep telling people in the office when they, one day things are going to break down. You're going to come to me and say, oh God, it doesn't work anymore. What do we do? And my response would be, well, we need to develop a new theory. So give me 10 years, we'll go away, do some observations, and we'll come up with a new theory. Is that okay? And I don't think they'll be very happy about that. So we need to think about how are we going to deal with this, where we've got blending heights that actually are going to vary. The height of it is going to vary according to the stability and also to the heterogeneity length scale. How are we going to put that in our models? Because anything below that blending height, by definition, you can't have a single value. So how are we going to evolve this? How are we going to evolve and be able to change the height of that boundary layer, or that blending height? The other thing is urban areas. So again, I've just got a conceptual picture here from building design. Urban areas stick into the atmosphere by quite a long way. Now, again, that's not all below the first atmospheric model level, even in coarse resolutions. So in actual fact, we've got surface elements which are actually going into the atmosphere. So having a simple surface exchange model which works at the bottom of the atmosphere just isn't valid for those environments. So we need to think about how do we put a surface energy balance in multiple levels of the atmosphere. Now, if you take an explicit coupling approach, which often is done in like the US, yeah, you can do that. It's not too difficult, but there's going to be limitations in terms of your time step. You're going to have to run with very short time steps, and if we're looking to go into high resolution, that could be problematic. It's going to cost you a lot more. If you start taking the implicit approach, which a lot of the Europeans take, then you find that the equation set becomes so bad so quickly that it's almost impossible to solve. So again, how are we going to solve this to actually put these distributed surfaces within the atmospheric levels? Okay, so those are some of the issues we face. What about other things? Well, we saw yesterday with hill slope processes. As we go to higher resolution, we need to resolve where the water's going in terms of these hill slopes. Now, we know that you get enhanced precipitation due to orographic enhancement. So you're going to get more rain on the top of mountains than you do in valleys. Now, Jan Polsch has done some very simple modelling where he's looked at evapotranspiration, both in valleys and on hills. And we find that it's actually the increased wind speed, giving increased turbulence at the top of the hills, which gives you more evapotranspiration. So you've effectively got a more active water cycle at the top of the hills than you've got in the valleys. So if we just take the 1D approach, what you're going to end up is wet hills and dry valleys. And that's not realistic. So we have to do three-dimensional processes here. We've got to resolve these things. And Andreas showed a great example yesterday of where this becomes really important. If you don't get it right, your temperatures are going to be wrong. So that involves both the way the water moves through the soil. So you can see this picture at the top here. You've actually got water along that slope that comes along, and eventually the water reaches the surface, and it can actually go as surface flows. It may be into a river, or it may just be, if you're at the top of the mountains, it's really wet sometimes. You see it's quite wet actually on the ground itself. So the way the water moves through that system is going to be important. But the other thing as well is the water availability to vegetation is going to be different. So at the top of the hills, you're going to get areas which aren't saturated, and at the bottom, they're going to be saturated. And that's going to change your Bowen ratio. So that's going to change your, if you like, your boundary condition to the atmosphere. But along with that, how the water moves through that environment organises how vegetation appears on that landscape. So you look at some of these pictures here. If you look at the top left, there's a semi-arid environment, and you see this vegetation is growing in the valley. That's because that's where the water is. So the water has moved down into the valley, and that's where the vegetation is. If you look at the one on the top right, you can see you've got vegetation down some strips, and that's where the water is going down the hills. But it's not just with the water, it's also the aspect. If you look on the right-hand side there, there's several pictures of where you've got the northern slopes on the right-hand side and southern slopes on the left-hand side. And depending on whether it's energy limited or not, depends on where your vegetation grows. Now, if we're getting down to that stage where we're resolving some of these things, we need to know where that vegetation is going to be. So we need to be able to model that. So another aspect we need to worry about is river routing. Now, river routing doesn't necessarily follow regular grids that are used for atmospheric modelling. So we know that it tends to go along where the slopes are. And if you talk to hydrologists, they're quite used to this. They have very irregular grids, and it can be quite complex, like you see with this picture on the left-hand side. You can see where a river is there, but it's quite a complex network that they're using to do that. Now, we can simplify things, and again, Jan's done some work where he's done this sort of catchment scale, and you simplify the problem down into smaller regions where you can route the water, but it's still non-uniform grids. So we're having to think about now, how do we do these different grids? How do we link that to our land modelling? And I should have said before, when you got the three-dimensional for the hill slopes as well, that doesn't necessarily follow atmospheric grids as well. That's following your terrain. So again, the soil processes don't necessarily follow the regular grids that are imposed on us by the atmosphere. So we need to think about how we might want to run some of these land processes on completely different grids. And then we've got to think about how we're going to connect all that together. So that comes back to defining clean interfaces between these different modules, if you like. Now, again, when we come back to the implicit coupling of the surface to the atmosphere, we tend to need to have the surface exchange on the same grid as the atmosphere for the convenience of solving the equations. But I've just said, for the soil processes, we might want a completely different grid. Now, the soil is the part that contains the information in terms of the water limitation for transpiration. But the transpiration is done in the surface exchange. How do we get that information between those two parts of the system. And in fact, there's actually some developments that are being done now where you can't even separate that in terms of the way the vegetation processes are modeled. So we've got some real challenges here. How do we define these clean interfaces which allow us to do the modeling on the appropriate grids that it needs to be done on? And I said before that hydrologists have a lot of experience when it comes to particularly some of the soil modeling and some of the river routing modeling, but they tend not to do thermodynamics. Now, from our perspective, we need to include the thermodynamics. We can't do permafrosts if we don't have thermodynamics. How do we deal with all of that? So, yes, the hydrological community have some great knowledge, but it's not the end of the problem. So we need to come together as two communities. We need to work together. It's the only way we're really going to crack this problem. And then there's groundwater processes as well. So I'm not talking now about the shallow groundwater. I'm talking about the deeper groundwater. Now that controls effectively where your water table depth is. So is it going to be saturated at the surface or is that lower down? But it also depends on the timescale of which water moves through the system. And it can take a long time. And you can actually get flooding when there's been no rainfall recently. And despite what Julius Lingo used to say, that flooding is all about the rain, well, it is, but not necessarily at the right time. Because this can happen, days, months later, that suddenly the water appears in the rivers and you get flooding. So groundwater is also important. But groundwater is determined by the geology. And again, geology doesn't follow the grids you would have for atmospheric grids or even the soil grids. So again, we've now got a completely different grid that we need to worry about in order to do geological modelling. And again, we've then got to think about how do we actually define these clean APIs to actually exchange that information. Now, the surface and aquifer interaction. So we've got this water in the groundwater, and it's going to interact with the surface. Now, traditionally, we've said there's no two-way feedback by this. We have some water in the soil, we get some runoff, it goes into rivers, it goes wherever it was. Either we lose it from the system or it goes to the ocean or whatever. But it's all one-dimensional, or one-directional. That's not how these things work. There's actually some quite complex interactions between rivers and groundwater. And on the left-hand side of the picture is 3 different types of system. So in the top one, you've got effectively a stream where the surrounding land has actually got a high water table. And what that means is water is coming from that land and adding to the river. So it's actually increasing your river flow. If we look at the one just below that, we've got the situation where the groundwater and the water table is actually slightly lower. And so you actually get water going from the river back into the soil. And so you're actually losing what's in the river. And in the third situation, the water table is even lower again. And actually that water is again being lost from the river, but it's going through the soil system to get down into that water table. So if we're going to resolve things like hill slope processes, and we're going to include groundwater, we need to include these complex interactions with the river flows as well. Okay, so that's all very well. We've got lots of components. We're talking about why is that important? Well, if we accept, well, we saw before that if you have a different availability of water, you get a different Bowen ratio, you get different fluxes to the atmosphere will respond differently. So we need to be able to resolve or model the evaporation and the heat flux, the energy balance we're getting from these open water surfaces. And that includes rivers. So we've got rivers, dams, any lakes, anything like that, but we need to include the water. Now for some of that, things like lakes, we have schemes that do that. But when it comes to rivers, this adds another layer of complexity because it's no longer just moving the water through the river we need to worry about. We need, again, to think about the thermodynamics. So we're going to have to model what the temperature structure in the river is if we're going to actually get the energy balance and the moisture balance from that. And that's not easy because, we've then got to worry about all the fresh water going in, how it all changes. And I don't know any of the river routing models we've got at the moment that do this. But it's going to be really important to get those right fluxes, particularly when we're going to high resolution. So now if we accept that open water is important because we need to resolve it, we don't need to just worry about rivers, we need to worry about inundation. So this is, say, when you have a river overtops its banks, and you get a lot of water covering that land. We need to be able to model that and know that the whole of the energy balance and the water balance has changed. it's going to feed back on the atmosphere, particularly when we're talking about high resolution. But these schemes tend to be, they tend to have things like variable time steps for convergence criteria. And if you're not careful, if you just try and apply one everywhere, you'll find that your time step goes to 0 if you're on fairly steep slopes. So you can't actually run it everywhere. Because what it's really saying is that inundation isn't appropriate where you've got steep slopes. So we can't just have a model we apply for. We've got to think about where do we apply it. So we may need to have variable grids or even limited domains, which means we've then got to interface that somehow with the stream flows and everything else. How do we do that? These are technical challenges we have to worry about. Now, there are some river routing models where you can combine that with inundation. So there are some things out there we can use. But we've got to think carefully about how we're going to do this. I've just noticed, I think I'm rushing through this really quickly, so you've been plenty of time for questions. But anyway, so then we go further, we talk about urban inundation. If we think about climate services, this is a really big thing. This is where most people live now. With over 50% of the world's population now live in cities. And if we're worried about urban inundation, this is the thing that really impacts on people. But urban inundation is a completely different scale again. You're talking about resolution of about 10 metre. You have to resolve the buildings that you've got in the city to be able to worry about urban inundation. And that requires an awful lot of information about building design and how that's done. Now, traditionally, these models are run in hindcast. They tend to be run and say, if we had a certain precip scenario, what would get flooded? And they say that the people do this because it's far too expensive to run these models. But it's always struck me that this is what the hydrologists say. Now, is a hydrologist too expensive to run real time the same as a meteorologist? We're running some quite expensive models. Are these inundation models actually that expensive? I remember talking to Andy Brown once, and we were saying that the land doesn't really take much of the computational runtime for the model. And I said, well, actually, I think it's my challenge to try and get up to 10, 20% by making these, by actually capturing these features. But again, we don't want to be running these inundation models all the time because they are expensive. So we've got to be able to turn them on, only run them when we need to. Now, the obvious thing is say, well, you do it post-processing. You can just run it when you need to then. But that's missing the point I made before, that it's important that we get the open water to get the energy balance right. So if you're going to resolve these urban areas, you have to have this in the coupled system. Otherwise, you're missing the processes that are going on. Tidal zones. I think someone mentioned this before, but in tidal zones, you get wetting and drying of land. So sometimes it's completely wet, and other times it's sort of a slightly drying soil. Now, this links with the wave and the ocean models. Whose responsibility is it to do tidal zones? Is it the land's responsibility? Is it the ocean wave model's responsibility? Very difficult to answer, and we need to come together as a community to try and decide how we do this. So, do you take this in terms of the land and say, well, actually, we'll have a sort of a wet tile and we'll have a dry tile and we'll dynamically change the fractions between the two as the tide goes in and out? Or what about where you've got very shallow water? With the sort of things that ocean models use, the bottom boundary condition usually is like a zero flux boundary condition. That's no longer valid when you've got very shallow water. So you actually have to put a soil below that. So it's no longer something that, this is your responsibility, this is ours. We have to work together to see how we're going to actually solve these problems. And then if you thought that was bad enough, we have to worry about human activities. Now, the human influence on the terrestrial water cycle is very significant. They've not only put in things like dams and reservoirs, which is changing the whole flow of the rivers through the system, but they've put things like irrigation. So we're taking water out from somewhere, we're putting it into crops and that. And the whole reason is that it's going to change the energy balance and the water balance. In order for the crops to grow, they need the water. You've got more evapotranspiration. But that water then has to come from somewhere. So it either has to come from groundwater extractions, in which case you've got less water in the soil, or it comes from the rivers, in which case you've got less water in the rivers, which means when you're thinking about that sort of boundary condition for the freshwater fluxes to the ocean, that's going to be affected. But what makes it even worse is these decisions in terms of human activities are not made according to the physical environment. They're made because of socioeconomic or even emotional decisions. And it often strikes me that there's the two disciplines I can think of where people make forecasts. In the weather and climate, we make forecasts, and everyone expects us to be perfect every time. If you think about economic forecasts, when they do forecasts, nobody expects them to get it right at all. Now, we are moving from that domain where everyone's expecting us to get right to go into this socioeconomic where people always get it wrong, and we're still going to be expected to get it right every time. So how are we going to deal with that, with all these human activities? And there's another problem. We need ancillary data to run these land models. We need to know information about the surfaces. Now, a lot of the data sets we're using are around the same resolution of the modeling we're talking about. They're around 1 kilometre. So how are we going to get these sub-grid scale features that we need to resolve if we haven't got the data that tells us what they should be? But it's even worse than that. If you take some of these data sets, so you look at the picture on the left-hand side, these are 2 soil databases. And shown on there are the sand, silt, and clay fractions that you get from them. And if you look at something like the Sahara, you can see they've got quite vastly different sand fractions for the Sahara Desert. You would think that was really easy to get right, wouldn't you? But they don't even agree on that. And then you look on the right-hand side, this is a figure of the agreement between 4 different land cover data sets. And again, there's areas where you've got full agreement. It's sort of Greenland, we know that's icy. But you start looking at some of the vegetation areas, some of it's going down to either no agreement or actually very low agreement. So we can't even decide what the land cover should be from these databases. How are we going to get this information that we need to run these models? Okay, so it comes to some conclusions here. So first of all, we can't assume that the current theories we've got are going to be valid for high resolution. They're not. They're already breaking down. And at the moment, we're getting away with it. But the problem is we have no alternatives, or some of these things, we have no alternatives. And that worries me. Because, are you, as I say, as an atmospheric community, are you going to wait for 10 years for us to come up with this before you make any further progress? I don't think you'd be happy with that. So we need to do something on that. We also then need to think about, when we go to high resolution, we're having much stronger moisture convergent and divergent zones. And that means we have to be able to model the 3-dimensional structures on the land to be able to resolve that and get the water into the right places. Now, I said the hydrological community have a lot of expertise in this, but it's not the whole answer because, as I said, they don't do the thermodynamics. So we really do need to bring these 2 communities together. Traditionally, we've been tackling the same problem, but we've been looking at the different aspects. The land surface modelers have been trying to get the right fluxes, and the hydrologists have been trying to get the right stream flows. It's the same problem, just the different end of the spectrum. And I've often given talks with the hydrological community where I said, your models are wrong. Because I'm sure if you looked at the surface fluxes, they wouldn't be right. Your stream flows might be right, but your surface fluxes wouldn't be. So your model's wrong. But our models are wrong as well. Because we might be able to get the surface fluxes right, but we won't get the stream flows right. So none of us can do this properly. So we need to come together, share our knowledge, and tackle this problem as a whole of the terrestrial water cycle. We've also got some technical challenges. So we're going to need to run these models on different grids. So soils, the river routing, maybe the inundation, we've got the geology. They're all going to need to be on different grids. So we're going to think, we've got some science challenges in terms of how do we define the information that's being exchanged and have a clean APIs. But we've also got to think about the technical challenges. There's a lot of work now thinking about how we use atmospheric models with GPUs and next generation modeling. No one's really thinking about how we do that with, say, inundation models and maybe with the land components. The best we've got at the moment is we run it on a different grid, which means we don't have to worry about it anymore. But unfortunately, we do have to worry about that. And it may be, though this is where I get my chip on my shoulder, it may be that once we've got different grids and we're having to couple with, through couplers or something, people will actually stop saying, we did atmosphere-only simulations, because you didn't. You did atmosphere and land, or atmosphere and surface simulation. You cannot do an atmosphere-only simulation. Still got a surface, in some way. But anyway, yeah. And then we get to the human activities. It's not just the physical environment we're having to worry about. We're having to worry about socioeconomic modelling. You think about something like irrigation. Irrigation isn't done optimally for the crops. is done for convenience or economic reasons. You know, it might be flood irrigation, drip irrigation. There's a whole host of reasons why it might be done that particular way, but it's not done to optimize crop growth. So we need to worry about all those decisions. And then finally, do we actually have the appropriate ancillary data to support these ambitions? And I would sort of say at the moment, the answer to that's no. And I don't know what we do about that. How do we get higher resolution data? We struggle with the resolutions we've got now. Things like the soil databases, we've got some good regions in the world. So Europe's pretty good, the US is pretty good because we've got good surveys. You go to Africa, it's really poor. So how do we do the high resolution with that? Okay, so that's the conclusion, but I wanted to come with this a summary slide. And this was something that Jan said he wanted to really emphasize here. And that's when you go to increasing resolution, for the atmosphere and the ocean, they're fluids, they mix. So as you go into high resolution, what you're doing is you're actually resolving more processes. You need less parameterizations. And I've heard it said already this week, you know, what we want to do, we want to get to high resolution where we don't need the parameterizations anymore. It's the opposite for the land. The land is a solid, it doesn't mix, or at least not on the timescales we want to think about. And so what it means is that the processes that we used to be able to neglect, we can no longer neglect. So we need to be able to put more parameterizations in. And you may have noticed here that I've done a whole presentation and I haven't shown one model result. Everything has been conceptual. And the reason is because none of this is in our models yet. So you talk about running high resolution. You can't run high resolution with the land yet because the things aren't there. So all you're doing is running high resolution in the atmosphere and hoping the land is okay. Well, it's not. But there's a heck of a lot of work that needs to be done. I was thinking about this morning, and I was thinking with the resources that we have at the moment that do the energy and water, you know, how long would it take us to put this in? And I think it's something like 10 to 20 years, the resource we've got at the moment. So again, are we going to wait 10 to 20 years before we can really do high resolution modelling? So this is a real problem that we've got within the land community. The carbon community maybe have got a little bit more resource because it's, you know, it's what Christian has often called the sexy science. It gets the funding. The energy and the water doesn't. We have very few people. We don't even have people, very many people at universities that deal with this, where we can feed through to get this. So it's a real problem in terms of resourcing as well. So on that lovely pessimistic note, I'll stop there and take questions.
There we go. Yeah, that was a great presentation, Martin. There is an answer to one of the questions you posed. One answer to it. There's probably an infinite number of possible answers, but in some of my colleagues' work here at NCAR, we've developed a system called WRF Hydro, which many of you may have heard, and we tend to run it today with sort of a 1 kilometer land surface resolution scheme and like 250 meter routing, so pretty high resolution compared to what we're used to in the land atmosphere world. And talking to my colleague Dave Gotchis, a rule of thumb, and it really depends a lot on how you configure things, but a rule of thumb is it's about 25% of the WRF system. So if you run them together, it's like 125%. So that's a full-on hydrology model. They share a land surface model. There's no MP in both cases, but that's full-on. So it's like a quarter. And you can, of course, change that by setting different resolutions and things. But, you know, in an interesting question that we're just starting to look at now in a project we have collaborating with USGS is, what does it look like when you fully two-way couple the hydrology and the land atmosphere? And what does that look like? Because typically the hydrologists will take whatever atmospheric forcings come to them. And this is something, it's kind of buried in what you said, but I don't know if you singled it out explicitly. Invariably, there are always biases the hydrologists are worried about. So they will bias correct whatever atmospheric data you give them as an input. And when you couple, you can. So very well, possibly, and I would predict actually almost with certainty, you'll make the hydrology way worse. So you're probing all the right issues, but anyways.
Yeah, I think you're absolutely right. It's only when we put all this together we'll realize just how bad we are.
Yeah, exactly.
But it's the first step.
Yeah, yeah.
You know, of doing this. And it always frustrates me when the hydrologists say, well, we want potential evaporation to run our models with. And I keep saying, well, can you evaluate it? Can you know, where are the observations? Because it's a theoretical concept. How can you run your model with a theoretical concept? It makes no sense. We're beyond that now. 20 years ago, maybe that was a good idea, but surely not now.
Yeah.
That's why we need to bring these communities together and share our experience. And as I said, I think it's only when we do that we'll find that we're both a lot worse than we thought we were.
Yeah.
And then we can do something about it.
Well, yeah, I think there's great opportunity. And I'll just remind, Linda Mearns isn't here, but yesterday she says, well, what does an interdisciplinary team look like and how interdisciplinary is enough? So anyways, thanks.
I want to poke a few holes in your pessimism, and then I'm going to work with you to plug them again. But so from an applications point of view and wanting to know the hydrology and all that, I believe everything you said. Okay, but the Met Office is running forecasts every day at 1.5 kilometer with what you describe as completely inadequate land surface schemes. Are they all crap? Are all these forecasts crap because of the inadequacy of the land surface?
Well, you might find they're not. So a good example, we've been doing some work with the observational campaign we did down in Spain, Liège. And a good example there is with irrigation. So we had a sea breeze that arrived at the site during the afternoons. And if we run our mid-scale model for that area and we don't have irrigation, the sea breeze arrives too early. If we put irrigation in, the sea breeze arrives pretty much on time.
Yep.
We don't have irrigation in our operational model at the moment. So it probably depends what you're looking at.
Yes, so I think that's where we start plugging the hole again. So my point is that not all of this is as important as something else. So the real question I have, rather than are your forecasts crap because your land surface isn't adequate, is what are the high priority items in your list and what are perhaps the lower priority items? How do we get through this mess? We can't just say we need to do everything, because then, every sphere can make that argument. So the real question is what will likely have a large impact? So we saw the mesoscale systems over the US being depending on groundwater in Andreas's presentation yesterday. So that could be a high priority item, have at least a simple representation of that. But the deep groundwater, I'm sorry, I don't buy it. I don't think we need to think about that for the next 10 years to build a climate model. Honestly, I don't believe you, actually. So there's shades of gray here, and we really have to prioritize what are the... So where would you start, and what would you leave for now?
I think the first thing, the things that worry me the most are where our theories are no longer valid. Because I say at some stage this is not going to work. And I think we already see a little bit of evidence of this in that we're not getting enough variability between surface types with the heterogeneity because they're too closely tied to a blending height which is too low. Now, okay, with the forecast, there's so many other uncertainties, you probably don't see very much. But at some stage, it's going to go wrong. And what worries me is when someone comes along and says, what else do we do? I don't know, no idea. And that causes a problem. So I think those are, but I think the three-dimensional water transport as well is the other one. And I know things like no MP. So some models are starting to go that way. But as a community, we're not really there yet.
And what about the coupler? Since Patch is lining up behind me, I better get off the floor. But how about the coupler, the technical side? So that has been debated as long as I've been in the field, that the land surface should be coupled through a coupler, shouldn't be coupled through a coupler, should be. Next year we should do it again, the year after we decide it's too hard because the implicit solvers for the boundary layer get screwed up. And then we want to do it again. So where are we? Is this going to provide new impetus?
So part of the hydrojoules project that was done, we actually did some thinking about how we would design this. And the idea at that time was something that they called the South African flag. So you've got three chunks. So your surface exchange would be tied to your atmosphere for the implicit coupling because otherwise it gets horrendous to solve. Rather than a 2x2 matrix to solve, you have 2 by number of grid points on your globe. So it becomes horrendous. So that was one bit, and then the soil could then be something completely different. And we're saying maybe we follow what the hydrologists do, or maybe we use something like hydrological response units, rather than the gridded structure. And so we can do something different. And then there would be the surface water component, where we've got river routing, inundation, again, could be a completely different grid. And we can sort of define the information that needs to be exchanged. But where they've made no progress on the hydrological since coming up with that, is particularly with the soil moisture limitation on transpiration. How do we get that information between those different parts? Because your soil model now might not have the vertical levels we have now. So how do you get this information about how much water is available in the different parts of the root zone and get that back to the transpiration? I don't know. That's something that's got to be solved. So there's science problems with this as well as the technical.
As your talk pointed out, land's a bit of a pain in the arse. So my question's about the atmosphere. The slide before this one, you talked about basically the finer scales. So as we go to finer scales in the atmosphere, we've got increased detail and increased intensity of precipitation. Yep. And we know that that's not necessarily predictable on the scales that it's interacting with the land. So one of the mechanisms you would do if you were a regional model and you were trying to understand the hydrology at a regional scale to get information, you'd run an ensemble. Do you think that you need an ensemble for land as a boundary condition for the atmosphere, or in a climate sense? Or do you think that it kind of averages out, and so you don't need to worry too much?
I don't know is the honest answer to that, John. What I would say, if you go to the impact side, which I haven't really discussed here, but at the end of the day, I would say, why do we do any of this? Well, it's for the impact, which is probably 90% land. So actually, land is the most important component. But anyway, so when you go to that situation, I think you do need the ensembles absolutely. Because your certainty, and a good example of this is some of the flooding events we've had in the UK in the last couple of decades. You can get convective summer precip, which is within 1 or 2 grid squares of where it actually occurred, which is perfect forecast. You can't do any better than that because of the way the numerics are set up. But it happens to be in completely the wrong catchment, hydrologically speaking. So the model would say there's no flood. And you get this catastrophic flood. So we do need to have some clever way of thinking about the ensembles and how we use that information in terms of the climate services. But whether we need it for the feedback of the atmosphere, I don't know at this stage. I think we would have to look and try and understand it and see how much we need and how much we don't.
That comes back to our conversation in the breakout yesterday, of course, of whether for impact studies we are mainly focusing on using a regional system driven by far better global models, or whether we want to do all the impact studies within it as well and things. So
no, I think you're right. We need to understand where the feedbacks are important for the circulation and getting the circulations right, and then the impact stuff can come from those regional models. I think you're right.
So I'd like to add to your list of things to do, and I'm not a land modeler, so pardon my ignorance here. Maybe you already have this, but newer ocean models such as MOM6 and MPAS Ocean are formulated such that they feel the heat content of rain and evaporation. Atmosphere models, as far as I know, don't take that into account. We're now working on putting that into the NCAR model. And it's actually one of the largest energy imbalances we have that we're artificially fixing, at least locally. So my question to you, are there land models who take this into account? Because what I understand, what the little I know about land models is it's not that straightforward to put into the model.
No, so I think this is where effectively when rain lands on the surface, it's sort of applied the temperature of the surface that it's on, which is a real problem. But we're stuck with, again, because the atmosphere doesn't tell us what the energy is in that. And one of the real big problems with this is warm rain events on snow, because you get a lot of melting. So it's the most sort of catastrophic melting events we get in the UK, where we got a lot of snow. You suddenly get a warm front come through, and not only you've got the warming, but you've got all this warm rain adding to it as well. But we can't do that because we don't know what the temperature of the rain is. Now, it's possible you could do something in an NWP sort of perspective and say, well, we'll take the liquid water temperature of the atmosphere and we'll say that's what the temperature is and we can melt from that. But you couldn't do that in climate because it wouldn't conserve energy. So how do we do this with the climate? Because you really need to know what the temperature of the raindrops are. And I think the atmospheric models are a long way off being able to do that. So you're right. So we just neglect it. But it does have an impact, definitely.
There seems to be at least in a climate run locally, those terms can be quite large. Like we're talking over 100 watts per meter squared.
Right.
Thanks.
Yeah. Thanks. Okay.
So before lunch, we're going to move on to a couple of contributed talks. And just a reminder, don't run away when we end the session. We're going to all go outside before we get lunch and have a picture. So next up is Aaron Donahue. Come on up to talk about ultra-high resolution modeling in E3SM.
All right. Make sure I get my bearings. Hello, everybody. My name is Aaron Donahue. I'm from Lawrence Livermore National Lab. And today I'm going to discuss with you the efforts that we've been doing in the Department of Energy to develop an ultra-high resolution representation of the E3SM model in the atmosphere. Before I start, I just want to acknowledge the fact that this is a really big undertaking, and all of the contributors to the results of this talk are listed there, and as you can just see, it's a rather large number. So I want to give them credit because they've contributed a lot. So, to begin, the simple cloud-resolving E3SM atmosphere model is an atmosphere model in E3SM that targets convection-permitting scales. And so that's illustrated here in this diagram by the 4 parameterizations and, of course, the die-core. So turbulence and cloud formation are handled by the shock scheme. Microphysical processes are handled by P3. Radiation by RRTMGP. And my colleague Ben Hillman will have a talk about RRTMGP tomorrow. And the aerosols are handled by the simple prescribed aerosol model SPA. The resolved fluid dynamics are resolved by the spectral element non-hydrostatic die-core HOME-XX. And of course, the key component is, since we are targeting convection-permitting scales, there is no parameterized convection. So before I continue the rest of my talk, I think it's important to illustrate 2 different acronyms, which I'm going to use throughout the talk so that I don't cause any confusion. So first, I'm going to mention something called EMXX. That's the model itself. It's the full infrastructure. It doesn't necessarily have to be run at these scales. But SCREAM is the configuration of EMXX, which specifically is focused on convection-permitting scales. So, some novelties of just EMXX, the full model, that I want to illustrate are that during the development of EMXX, and I'll briefly just mention that EMXX is a model that we've built from the ground up. So this is not an adaptation of an existing model. It is actually built from the ground up based on an older model, EAM. So that gave us a lot of flexibility, one of which was that we could focus on unit testing. And so each step of the way while we developed this model, we introduced robust unit tests, which gave us a stronger sense of trustworthiness for the model. And that's illustrated here in the figure on the right. There we are, which shows the results of a convergence study using the doubly periodic version of EMXX. And so this is a small scale domain, or just a small domain where we're able then to do refinement of the mesh without too much computational expense and do things like this convergence study. And this illustrates nicely how some of the aspects of our model converge like we would expect. And so this is just one application of this robust unit testing. Another thing I really want to highlight is our use of the C++ COCOS infrastructure. For those of you who do not know what COCOS is a library built in C++ by Sandia, and the intention of COCOS is to allow you to write a single code that has performance portability and is able to be run on both GPUs and CPUs without having to have any if-defs in your code or anything like that, and switching between OpenACC and CUDA. It's just meant to allow for a monolithic code that you can hopefully pick up, take to a machine, and get running pretty much right away. And so this has allowed us to have excellent performance portability and given us the opportunity to really just push forward, and every new machine that's going to come out will be able to take advantage of, hopefully, very quickly. And I think that's an important aspect of EMXX. Now, speaking of GPUs, one of the key reasons why we care about GPUs is performance. And so here, I'm illustrating some of the performance aspects of EMXX. Now, I'll note this figure here shows GPU versus CPU performance, but a really key component is that this is at 100 kilometer resolution. So this is not the convection permitting resolution. That's because the scaling results for that haven't finished yet, and so I didn't want to present premature results at this conference, but those will be coming out soon, and when we write a paper, of course, we'll be able to illustrate those. But there are some key aspects that are still very important that we can see in these results at the 100 kilometer scale. First off, the two CPU lines, the orange here and the blue, are both just running CPU. The blue line is the original EAM code, which is written in Fortran, and the orange line there is the C++ version of the code Emacs, also running on CPUs. And basically what we can see is they overlap, that they have similar performance. But if we look at the GPU performance, we can see that there's a dramatic increase in the performance of the model. Here at the numbers aren't there, but here at 4 Summit nodes, and Summit is one of the leadership class facilities at Oak Ridge National Lab, this is about a 16 times improvement in the simulated years per day. And here, just because it's beautiful eye candy, we've actually been able to accomplish upwards of 100 simulated years per day at 100 kilometer resolution, running on a separate machine called Perlmutter, which is at at Berkeley National Lab. So these are very promising results for the benefit and performance in this new model. And based on preliminary results from our Summit runs at high resolution and these results as well, we're able to predict that we would expect about 0.7 simulated years per simulation day when running all of Summit, which is about 4,600 nodes at about 6 GPUs per node. Pushing forward and taking advantage of our COCOS framework, we hope to immediately transition to Frontier, which will be the next leadership class facility for the DOE. And there we expect to get something like 1.2 simulated years per day, which is a great accomplishment for a global 3 kilometer model. So based on all of these predictions, we expect to get around 8 simulated years per year. And what I mean by that is, a typical insight allocation, which is the program by which we get time on these machines. Based on what a typical insight allocation might be, if we were to burn all of those hours at these numbers, we would hope to get somewhere around 8 simulated years, which we believe can provide us with a groundwork for a lot of really good science at this high resolution. Digging in a little bit deeper about just performance in general, we can look at where the atmosphere is spending most of its time. And here we're looking at a figure of an actual 3 kilometer simulation. This is with a little bit over 3,000 Summit nodes running the high resolution Emacs model. And it's very obvious right off the bat that most of the time the model spends is in dynamics at about 87%. Radiation is the most expensive physics process at 8%, but it's still not anywhere near the 87% spent in dynamics. And this is actually a promising result, because the dynamics code that we are adopting has been proven for the last few years to be a very good code for scaling on GPUs. And so by seeing that it's the dominant process, this gives us the expectation that our model will also have good scaling properties on GPUs. There is something about Summit that's causing the die core to not perform quite at expectation. So we actually have a part of our team is looking at that, and we hope to actually see improvement in the numbers just because it looks like it's all in the die core, and we understand the die core very well, including its performance. So these are all very good results in terms of performance. Another important question is just how well does the model perform in terms of its skill? So that is what we're going to look at next. So as part of our development process, while we were producing Emacs and C++, we also adapted the original Fortran EAM code to run the Scream comp set, or to run the Scream configuration. That way, we could immediately start doing science with the Fortran code while we were anticipating having the C++ code later down the road. So the V0 is what we're calling it, Scream V0 results are actually quite mature. So those are the ones that I'm going to discuss with you now. But this figure here is just meant to illustrate, and here we're looking at a 28 kilometer simulation results. It's just meant to illustrate that the Emacs and the EAM code do perform relatively the same, at least by the eyeball norm. They look very similar. And so our hope and our expectation is that a lot of the results that we've already witnessed in Scream V0, the Fortran version, would translate well to the C++ version, which is something that we'll see hopefully shortly after our simulations finish. So I'm going to jump in and talk about just Scream V0 results. So all of the results I'm talking about from now on are the Fortran version. So on the good side, the Scream skill is actually quite well. With relatively little tuning, we see that from this figure, where we're looking at observations and we're looking at model results, that the clouds and precipitation actually match pretty well, especially by the eyeball norm. And this is without significant tuning, so the hope is maybe with some tuning we can even better improve these. Throughout the course of our study using the V0 version, we also found that going to higher resolution does address some of the issues that we see in the climate modeling community, things like precipitation intensity, vertical structure of convection, and Amazon rainfall. And for those of you who are interested in knowing more about these results, you're welcome to see this citation in James from 2021. But, of course, there are also challenges, and so those are important to discuss as well. So a major challenge that we discovered is that we noticed that SCREAM has difficulty with aggregate tropical convection, and that is illustrated in this figure here, especially here in this zoomed-in version image, where we see what we call popcorn convection. If this were as a video, what you would see is that these convective features would pop in and out of existence, which is clearly not physical. And so popcorn convection has become a challenge that we've been spending a lot of time trying to address, and we still haven't quite found the solution for it. There are other challenges, such as our convective anvils are too small, and we also witness a double ITC in our results. So there are still outstanding challenges that we're trying to address. On the good side, though, SCREAM V0 did do an excellent job representing the 2012 North American derecho, both at 3 kilometers and 1.5 kilometers. And if you're interested in knowing more about that, here is a reference also, I think, in James, for some of our colleagues. And this video here is demonstrating that. Going into just radiation, we see a few more challenges. For example, we noticed that there were not enough clouds over the Southern Ocean. There's not enough tropical anvil clouds, and again, we have that double ITCZ. So we still do have a lot of work cut out for us. So I'm going to conclude just discussing what our future plans are. So SCREAM V1, the C++ version, is just about ready for us to do science campaigns. Our intention is that this month we will start a 40-day seasonal simulation of autumn. Following that, we'll be able to do the Diamond 1 and 2 configurations. And then based on those results, and of course, any fixes that we have to add as our results illustrate maybe more challenges to us, we can transition into something a little more substantial, like a 3-year CES type run, where we can run with and without plus 4K SSTs to see the impact on climatologies from sea surface warming. I didn't mention it in the talk, but there are also ongoing efforts amongst other members of the E3SM community to go to higher resolution ocean modeling, higher resolution ice modeling. And so as those come online, that gives us an opportunity, hopefully in about 2024-ish, for us to do high resolution fully coupled model runs and see where that takes us. And of course, we would hope that all this output could become really freely available, because then some good science can be done on that as well. Now, over the next 3 years, there's also going to be a parallel effort to extend EMXX to be sufficient for running at coarser resolutions. The intent is for EMXX to replace EAM as the only atmosphere component in E3SM, so we'll only run C++. And so in order to do that, we have to extend support to coarser resolutions, because of course there are also ongoing studies at those coarse resolutions as well. Now, some interesting challenges that I think this workshop is actually is in a good position to address, and I actually was happy to see that in our breakout questions, some of these have already been brought up. But one is, of course, popcorn convection. I don't think that was in the breakout session, but feel free to you're welcome to add it, because it'd be great if you had some ideas. But really the other two, which is how do we tune a 3-kilometer model? This is still a very expensive model, and tuning is typically one of the most expensive operations you do. And then what do we do with the output? When we go to 3-kilometer global models, we're going from gigabyte size files to terabyte size files. And how do you write that? How expensive is I/O? Is that really going to be the performance sink? And how do we post-process this data? And how do we share this data with the larger community and store it in a good way? And I think that is just a significant technical challenge that I think we're all going to have to be ready for as we get into running these models for longer. So with that, I would welcome any questions. Thank you.
It's on? Okay. Yeah, popcorn. How severe your results of popcorn is? Yeah, maybe the many diamond results. Which one is popcorn?
This one is popcorn, yeah. So you're looking at it down here.
Okay, I see. Yeah, did you compare the other diamond result? Is this similar to other diamond results, or?
To be honest, I actually don't know. This work was from Chris Tarai, so I don't know the details of what he's been doing. My understanding is that it is something of serious concern. So I think that if it was very similar to the diamond results, maybe we would be less concerned about it. But I can't definitively answer.
Maybe in this 3 kilometer range is similar result, but if you cloud microphysics change something, but maybe if general behavior, you may quantify this popcorn result.
So we have been modifying both the macrophysics or the shock turbulence scheme, and also looking at the microphysics scheme and trying to whittle down on what could be the cause.
Hi, very nice talk. I have the impression now that E3SM was using club and is moving to shock. Is that accurate? And if so, can you say a little more about it?
I don't think it's accurate in the sense that the shock usage really is only the screen configuration. And as I mentioned before, we're also going to extend our our support for the coarser resolutions, which by no means would mean that club would be an absolutely fine model to also use. Although I will mention that EMXX is in C++, and so currently shock is the only macrophysics scheme that we have that's written in C++ Cocos. So for performance aspects, club would need to be transitioned into the C++ Cocos code.
Slide, I think you described shock as more advanced or
more
sophisticated or something like
that. I asked Peter Bogenschutz, who is the author of shock, about this bullet, and he wanted me to express that this does not mean shock is more sophisticated than club. He is referencing schemes that are used at this resolution in other modeling areas, but not club. So yeah, this was by no means meant to be a broadside against club.
Thanks for a nice talk. It was the future plans, really. So with the blobbiness, what do you call it, popcorn convection, and turbulence and microphysics and things. I guess in your future plans, we can reproduce this in a quite small regional model with some very, very cheaply. So have you got some kind of hierarchical experiments that you've got planned? Can you do a small region or regional refinements in the grid, I think, maybe?
Not yet, but that is also something that we're trying to develop. Yeah, so definitely when we finally put regional modeling, that's something that we can take advantage of.
It just seems like that really ought to be upfront in your. I think for everyone, we can't develop. We shouldn't be trying to develop global high-resolution models by running global high-resolution models, basically.
That way, that's the only way we can flex our muscle and look cool, right? Like, look, I ran like thousands and millions of computational hours. No, just kidding. No, I think you're absolutely right. Actually, I would just to Andrew's point, I think that the schemes themselves are capable and ready for that, but the infrastructure hasn't, because as I said, EMXX is from the ground up, so we need to adapt that part of the infrastructure to allow for regional modeling and make sure that things are being handled correctly. That's very technical, but it's just not in there yet.
Yeah, I just want to echo that. We didn't even do this for traditional GCMs, right? We had single column models, and we did a lot of work with them before we went to the full model. And we seem to be throwing all that away, and we don't quite know what to replace it with. But that wasn't my question. You didn't say much about low clouds. I mean, you have a different turbulence scheme than many other of the models that are being developed that are much simpler schemes. As
again, not my bullet, but
yeah,
yes.
All right. But the point is, apart from the Southern Ocean clouds, you didn't say much about low clouds. I sense that low clouds, as they always have been, are going to be a pain in the neck for everybody.
Yeah.
What do your subtropical clouds look like?
Actually, I do not know. Again, that's Peter
Time
Bogenschutz.
to check.
I will check, though. I'll get back to you.
So I want to comment on the popcorn convection problem. And I looked at tropical convection in the diamond models, and one model that's pretty similar to Scream, I guess this is ICON. Is it correct that this is an Fe3-based dicore?
No, it's a spectral element, so it's similar to the CAMS dicore.
Okay, I was under the impression this is Fe3-based. I would have said Fe3 in the diamond configuration did not produce popcorn convection, but ICON did, and I think one other model, but there were also models that were too clumpy, aggregating too much. So it's an interesting problem. There are a few models that did pretty well, and some were too aggregated, and some were too popcorn. So lots of work to do.
Yeah, thank you for that. That's a good point. Fantastic. Can we talk over popcorn? That would be very meta.
Thanks. Thank you.
Okay, this is a project involving a lot of people, including several in this room, Andrew Gettleman, Rich Loft, and Sherry Mickelson, and others you see named here, and even more. And I'd like to tell you that on Thursday at about midday, there'll be 2 more Earthworks talks by Rich and Sherry. And they'll be talking about the computational side of this. So I'm going to focus more on the results that the model is producing at this point. So this is a 5-year university-based project supported by the computer science part of the National Science Foundation. The goal is to develop a global storm resolving coupled model that uses a single nearly uniform grid for the atmosphere, ocean, sea ice, and land surface. So all components run on the same grid. And we think this is appropriate at very high resolution. So Earthworks consists of CAM6 with the MPAS non-hydrostatic dynamical core, which is developed by M-Cubed at NCAR. The MPAS ocean model developed at Los Alamos. The MPAS sea ice model, also from Los Alamos, which uses the CICE physics. The community land model, and CMEPS, the community mediator for Earth prediction systems, which we've heard about in some of the other talks here. Earthworks is not a project of CESM, but we are working to preserve compatibility with the evolving CESM code base, and we are also trying to engage with the CESM user community. So our goal is to develop the capability to perform 3.75 kilometer grid spacing, fully coupled simulations using GPU-enabled components with end-to-end workflow portability across a variety of computing systems, which I'll show you in a second. And initial objectives include porting MPAS ocean and sea ice into the CESM framework. Now, these models were working in the framework of E3SM, but CESM has a different infrastructure. And so a substantial amount of effort was needed to do this, and that was completed last year. I should say we're a little past the end of the second year of a 5-year project here. We assembled a fully working CPU-based version of the model, which I will show you results from here. I won't show anything from GPUs. We are in the process of making fully coupled simulations with relatively coarse grids, but getting finer every month, and I'll show you some of that. And we are testing and evaluating the MPAS dynamical core with the CAM6 physics at convection permitting scales, and I'll show you a little bit about that. We're also working to port most of the coupled model to GPUs, and you'll hear about that on Thursday. So these are the target platforms for now. We have others in mind too, but the results I'll show you today were all produced on Cheyenne. There's another machine coming, of course, at some point. We'll see. We're also running, or about to be running, at the Texas Advanced Computing Center, TAC, in Texas, and we've requested actually substantial resources on Frontera, which is a machine there. We have some resources at both NERSC and Argonne that we're using to test the GPU codes. So we're working to have workflow portability across these systems, and of course the idea is the code will run on both CPUs and GPUs. Okay, so here's a list of available simulations sort of by category, and I'll show you something from all 4 categories. So coupled simulations, including 30 kilometers, which we have some results from now. AMIP simulations with several different grid spacings. Regionally refined simulations for the Pacific Northwest and also the North American Midwest, US Midwest. And I'll show one slide with some aquaplanet results on it, showing resolution dependence of the convective precipitation. So, annual mean precipitation, let's start here. So on the top row on the right side, you've got observations from GPCP, and the other two panels there are results from coupled simulations with a coarse 120-kilometer grid and a 60-kilometer grid. If I was making the slides this week, I could put 30 kilometers on here as well. The bottom row shows results from AMIP simulations with 4 different grid sizes. And maybe the most interesting thing to point out here is that in the coupled simulations, the Western Pacific precipitation looks quite a bit more realistic compared to GPCP. Also, as we go to higher resolution from 120 to 60, or even in the AMIP runs, you can see the precipitation beginning to show up in the Indian Ocean better, in better agreement with the observations. So some improvement with increasing resolution as expected, and some improvement with coupling. These panels show simulations of the North Atlantic Oscillation. The text at the bottom right tells what you're looking at, but basically the observations are there from the European Center of Reanalysis, and we're showing results from both coupled and AMIP simulations, and they all look reasonable, and the percent of variance explained is in the ballpark of what the observations show. So this is encouraging. We're looking at ENSO, and we only have 10-year simulations. So you probably can't read the numbers at the bottom on the horizontal axis here, but this is 10 years at 2 different grid spacings, 120 and 60, and coupled, of course. And you're looking at the Niño 3.4 index that everybody shows. So the good news is there is variability, and it's on ballpark the right time scale. I mean, the simulations are too short to really say, but it looks at least somewhat encouraging. And hang on, before I go away from that, I'm going to show you some sea surface temperature and precipitation results. And for the model, they're going to be based on the transition between years 4 and 5. I don't know how to point on this thing. Top little thing, okay? So here, this transition. Oh, okay, yeah, laser would work better on the screen, wouldn't it? So between here and here, El Nino, La Nina, and the same thing here, years 4 and 5. So it's one event. And we'll be comparing with observations of 6 events. So here's the surface temperature over both ocean and land, and that's color, obviously, and then the sea level pressure anomalies are shown by the contours. And, well, I don't think we can conclude very much from this, but you can see some things in the simulation that look somewhat realistic. And this is the precipitation pattern. So I like the green stripe here. That's looking promising compared to the observations. But obviously we have to run this much longer to really draw any conclusions. Okay, I'm showing one slide with some aquaplanet results just to show you what happens with the CAM6 physics as we go to higher resolution. So these are aquaplanet with the colors showing different grid spacings. The legend is on the right side here. So the pinkish color at the bottom is a 7.5 kilometer grid. And so on the left panel, you're seeing the total globally average precipitation, which is basically steady and doesn't change much as we change the grid spacing. I think that's the main point. The convective precipitation is shown on the right panel, and it decreases by about a factor of 4 as we go from 120 kilometers to 7.5 kilometers. So the convective parameterization is being used, it's still there, but it's essentially not doing much as we go to high resolution, and that, of course, is what we want. This is not to say that this result is entirely satisfactory, but it's at least encouraging. A little more about what CAM physics does at high resolution. So these results are from a simulation with just the atmosphere and the land surface, not the ocean. And they show a case in which the grid has been regionally refined over the Pacific Northwest. So this is not globally uniform. It's, I believe, 60 kilometers away from the Pacific Northwest and 3 kilometers in the Pacific Northwest. So we're focusing on precipitation here. The observations are shown on the left. You can see the effects of the orography up in that part of the country. And then the second panel from the left is are the results obtained with Morrison-Gettleman version 2 with a 3-kilometer grid over this region. The third panel shows Morrison-Gettleman version 3, and Andrew tells me the main difference is the 3 includes Graupel. And then on the right side, we have the WRF physics. And I would say of the 3 simulations here, probably MG3 looks closest to the observations. WRF seems a little bit too intense to me. At any rate, this is a demonstration that the model can produce reasonable-looking precipitation patterns at high resolution, at least in this part of the planet. And here's a second case, again, regional refinement, this time over Central North America. You can see in the upper left here where the grid is refined. And so this is a forecast case. And started from observed initial conditions and comparing with observations. So on the left side, you have radar reflectivity from the real world. And the other 2 panels show radar reflectivity as computed from what the model is doing. And of course, there are issues about how to do that. The middle panel shows the results with WRF physics, which of course has a tremendous background of work with various mesoscale models over the years. And on the right, you see the results produced with the CAM6 physics with MG3, the 3rd generation Morrison-Gettleman scheme. And it looks, again, encouraging. Okay, so finally, I'm going to show you 2 movies. This is the second last slide. These are simulations with both coupled, both in the first year from startup. And on the left, you have 60-kilometer grid, on the right, a 30-kilometer grid. The runs were started from January 1. So on the left, the movie is going to run out to day 220. And on the right, it's going to run out to 230. And that's just a glitch with the movie making. It has nothing to do with the simulations. So the movies are going to play one at a time. And you're going to see a number of things. So here's the first one. 30 kilometers, relatively fine resolution. And by the time the movie stops, these are 5-day averages, by the way, so not that many frames, you can see the expected tropical instability waves, I believe they're called, along the equator. And you can also see the seasonal warming, or the shift of warm SSTs from the southern hemisphere to the northern hemisphere. We're in August, I believe, at the end of the simulation. Now we'll play the same thing, more or less, from the 60-kilometer grid. And again, you can see the tropical instability waves, and when it ends, it's not as warm. The seasonal warming in the northern hemisphere is not as strong as with the 30-kilometer grid. So, you know, these simulations are too short to really draw too many conclusions, but we're able to run the 30-kilometer model now, and in fact, it's gone about 1.5 years. It went a little further over the weekend. So, summary. MPAS, ocean, and sea ice have been successfully ported into the CESM software framework. We have made fully coupled simulations down to 30 kilometers, and a bit more than 1 year with 30 kilometers. We'll be running 15 kilometers very soon, maybe before the end of this month. MPAS, I didn't say this, but MPAS atmosphere and ocean can now be run on GPUs, and you'll hear more about this on Thursday. CAM uses club, which I asked about after the previous talk. We're waiting for that to be ported to GPUs, but once that's done, the CAM6 physics will run on GPUs. We're, of course, using RRT MGP. We are doing tests, which I showed you, of the behavior of CAM6 physics on convection permitting scales, 3.75 kilometer mesh. And our goal for the end of the project in 2025 is that the model will produce at least one simulated year per day on a 3.75 kilometer grid. So we'll see, but that's where we're headed. Thank you.
Hi, thanks for the talk. You've presented a lot of really nice progress. You described the Earthworks project, I guess, in quite technical terms. So the goal is to get a 1-year simulation going. Does Earthworks have a sort of science plan associated with it? So I guess the quick question is, in order to do what?
Well, first of all, our goal isn't just to be able to do 1-year simulation, but I was talking about the rate at which we could do a year there. So we certainly intend to run longer than a year, but exactly what we can do will depend on the resources we can get our hands on, and we're working on that. The science goals I didn't present here, but there's a broad range of things, including both climate and weather. So this is a collaboration between the climate side of NCAR, the weather side of NCAR, and CSU. And one thing that I'm particularly interested in is the behavior of both the convective and orographic gravity waves and their effects on the upper atmosphere. We intend to do simulations in which we can simulate the effects of such waves on the stratosphere. But there are many other things.
You told us at AGU that you were aiming for the same grids in each component, for instance, the ocean and the atmosphere. Yes. Can you, despite that, can you change resolution in each component? So run the atmosphere with a lower resolution ocean and vice versa?
Yes, CMAPS, which is the mediator we're using, the coupler we're using, is capable of interpolating between essentially arbitrary grids. So we could, for example, refine the atmosphere grid in one way and the ocean grid in another way and couple them, or just simply run them at different resolutions. That's all possible, but that's not part of the stated goals of the project. The goals of the project are same resolution for all components, globally uniform.
Yeah. Thank you.
On your plots of annual precipitation, I noticed that the AMIP type simulations had a very strong southern hemisphere ITCZ and that it got worse with decreasing resolution. Do you have any idea why
This
that?
is the precipitation you're talking
Yeah,
about?
the annual precipitation, your very first result.
Yeah.
Yeah, that one.
You're talking about the SPCZ precipitation?
Right, yeah. It looks like it's a lot more intense than GPCP.
Yeah, and it extends further east. So, you know, this can be an aspect of the double ITCZ problem. And I think that would be my initial interpretation.
Okay, thanks.
Thank you. Yeah, so today I'm going to present some results from the K-Scale project, which Hugh Lewis described yesterday afternoon. Got all my co-authors listed here, and it's kind of quite a large project now at the Met Office, so there's credit to all of these people listed on the slide as well. And I'm going to ask a slightly different question perhaps here and look at some of our tropical channel simulations that Hugh described yesterday and compare them to our traditional limited area model approach of running at high resolution in the tropics. So seeing whether by explicitly simulating convection across the tropical channel, we see added value from that compared to the nested LAM approach. Get the pointer going. So yeah, this is our model setup for these simulations. So in the purple box here, we've got the what we call the proto channel. So it spans 170 west to 170 east, 40 south to 26 north. So that's got 14 times as many grid points than the currently operational Met Office global model. So these are expensive simulations, and they do take quite a lot of effort to run. And then we've got 3 what we call continental scale limited area models, one focused on Southeast Asia, which is approximately the same size as what we run in near real time with our partners in that region, and then one focused on Africa and South America as well. And the thing about all these simulations is they're nested inside a 12-kilometer parameterized convection parent. So in the same way we would nest our regional models inside a parameterized convection global or parent model, we're nesting all of them inside the same model here. In terms of vertical resolution, we've got 90 vertical levels here for all of the configuration, and they're using the RAL3 science configuration. So that's the latest regional atmosphere configuration developed at the Met Office, which includes the new CASIM double measurement microphysics scheme and the bimodal cloud scheme. And the results I show here are actually for a 12-day case study period, but we removed the first 48 hours of the simulations to allow for convector spin-up. So we just focused on the 10-day period in early January 2018. Just to give a little bit of background on what was happening with the meteorological setup at this time, we've got the MJO plot on the left, where you see the MJO is propagating eastwards across the Indian Ocean towards the maritime continent at this time. It was actually sort of moderate amplitude in early January and then gaining strength later during the month. And then on the right, this was tropical analysis drawn by our operational meteorologists. So you can see the convectively coupled Rossby waves propagating across Indian Ocean and maritime continent, and also 2 tropical cyclones there, Ava towards Madagascar and Irving in the Indian Ocean, which I'll describe a bit more later in the talk. So yeah, getting down into some results and comparing with the observation, well, the satellite-derived precipitation fields from GPM iMerge. So we see with the MJO propagating eastwards, you've got enhanced or active deep convection across Southeast Asia, as we would expect. And then you can see the tracks of the tropical cyclones across the Indian Ocean and the kind of diagonally driven deep convection across South America as well. But if we look down at the bottom at the meridional mean sense, then we're starting to compare these observations to the model. So the black lines, the GPM iMerge observations, and then the red lines, the proto-channel, and each of the limited area models is shown in blue. So if we look towards the, I think what hopefully you see, agree to what I say, is just towards the center of the limited area model domains, you see quite close agreement between the LAMs and the proto-channel, and also quite close agreement with the GPM iMerge observations. When you go towards, when you have more influence from the lateral boundary conditions, so for example at the edges of the Southeast Asia domain and towards the eastern side of the South America and Africa domains, you see larger differences between the modeled precipitation values and the observed. So just to say a little more, the reason for focusing, at least initially, on precipitation is that we know this was a period where there was flooding and hydrometeorological hazards across kind of Southeast Asia, which was the original driver for this case study period. So if we focus in a little on South America, and Hugh began to describe this yesterday, looking in a little more detail, I guess, here. If we look at the 2 middle panels, so where we're comparing the models with the GPM iMerge data, the blue colors here highlighting that both the proto-channel and the South America LAM are really overestimating the precipitation within the Atlantic ITCZ. So this is just 10 days worth of simulation, but we can already see overestimation of accumulation of sort of up to 50% of the GPM iMerge values there, on top of 50% additional rainfall. I put here that, so going on to the right-hand panel where you compare the 2 models to each other, you can see comparatively to the model OBS differences that the differences between your 2 models are relatively small. And you also have some hint that the kind of structural change in the ITCZ with a wider and less intense ITCZ in the proto-channel. But obviously, we would like to check the robustness of that result with some more simulations, which we will do, as you'll see in the future work section. And then looking at perhaps the most, oh, got a bit of a black box, never mind. If we look at the animation in the bottom left, this is Cyclone Ava, which made landfall in Madagascar in early January 2018. So the animated loop in the bottom left is from the 2.2 kilometer proto-channel simulation. And if you use that alongside the wind gust in the second, try and use the pointer, could go wrong. Oh, there we go. So if you use that and compare against the observed track intensity of Ava, we can see we're producing a realistic intensity of the tropical cyclone. It's making landfall in a similar position to that which was observed, which, considering we're looking at lead times of 6 to 7 days here, is encouraging. And then if we compare with the Africa LAM, where the storm initiated outside of the high-resolution domain in the parameterized convection channel, you have a significantly weaker... Oh, that wasn't quite what I was intending. If you look here, you've got a significantly weaker storm, which is not too surprising given it's spinning up in the parameterized convection region, but it doesn't impact Madagascar in the same way. So you know, this is starting to see the benefit of explicitly simulating convection across a wider area by getting more realistic tropical cyclone simulation here. So if we think again, if we move region again to the Southeast Asia area and look at some of the, again, the differences between the modeled and observed precip, then we can see that both simulations in the West Pacific, again, if we look, yeah, kind of in the West Pacific region here, you see the blue colors indicating heavier rainfall than observed across the West Pacific region. Again, a familiar result from already the couple of days of talks we've seen. But then if we look along the western side of the domain, perhaps slightly more nuanced, is that you see a change in the sign of precipitation biases. So in the Southeast Asia LAM, where precipitation or convection is propagating in from the Indian Ocean to the west as the MJO propagates east, you see dry biases in the Southeast Asia LAM, so the red colors there, the western side of the domain. And then when you explicitly simulate convection across the tropical channel, you see a reversal of that bias to actually see wet biases in the proto-channel, particularly if you look kind of the west of Sumatra. So one of the other areas where we might hope or indeed hypothesize that we see improvements from explicitly simulating convection across the full channel is looking at propagation. So I've highlighted on the right-hand panel some of the biases that I've described in the Southeast Asia LAM. But in the central panel, you can see from sort of 7th of January, so that looking at longer forecast lead times, you see an enhanced area of convection propagating eastwards across the Southeast Asia region. In the proto-channel, there's no evidence of it in the GPMI merge, but there's also no evidence of it in the Southeast Asia LAM. So one of the areas for future work would be to target a period where we know there's enhanced convection propagating across the region, and looking to see whether we see differences in that propagation by explicitly simulating the full channel rather than just the Southeast Asia sub-region. I wanted to, for results, I wanted to leave with something perhaps a little bit thought-provoking and maybe to prompt some discussion. The arrows here are showing the impacts of changing the domain size as you go from top to bottom. So this is the proto-channel at the top to the Southeast Asia LAM at the bottom. And then the impact of upgrading your model physics is going from left to right. So you can see that if you look at the rainfall biases, they're fairly persistent as you, there are differences as you approach the model boundaries of the LAM domain. But the key, I guess the key factor is that some of those persistent biases can be significantly reduced as you upgrade your model physics from REL2T on the left to REL3 on the right. Whereas, for example, the West Pacific wet biases are quite resistant to explicitly simulating convection across the channel or changing your domain size if you prefer. So a caveat, the conclusions to start with by talking about the limitations here. So this is, at the moment, we're looking at a single day case study. As you'll see on the next slide, we have future plans to kind of expand that. But with a 12-day case study, one of the things to remember is that the upscale impact of explicitly simulating deep convection across the tropics will take time to impact on the large-scale circulation, so we really need some longer duration case studies to kind of investigate that further. But what we have seen here, and what's been highlighted, is that stubborn model biases, for example, the the over-intensity or the excess precipitation within the ITCZ regions can be seen in these short-duration simulations. And we do see more accurate forecasts by explicitly simulating convection across the channel for specifically Cyclone Ava, but with the expectation we might see it for other tropical cyclones as well. And then where we saw the greatest differences or the greatest impacts of explicitly simulating convection across the channel was in the regions close to the land domain boundaries, if I can get the words out. So I'll talk about that last bullet point here as we look at the current and future work. So Hugh yesterday showed some early plots from the cyclic tropical channel, so the full tropical belt with no east-west boundaries, and that's really opening up new doors for us because we can now propagate tropical waves without truncation at the east-west boundaries. So the longer duration simulations will now follow from that. So doing some longer 40-day to seasonal length simulations in the coming months, or at least starting them. And then we've also got the capability now to run N2560 global grids with explicit convection. And so we'll be doing that alongside these tropical channel simulations so we can start to think about tropical, extratropical interactions. And one thing I didn't say at the start was that these runs are using 24-hour updating SSTs rather than coupled with the ocean. So we'll also be doing some coupled simulations with the UM and NEMO for the ocean. So I'll just leave this slide up, but to say, looking at future opportunities, we are looking at our next generation modeling system. So it will be called, well, it's currently called ELFRIC, and it's using a cube sphere grid rather than the current lat long grid. So it opens up our opportunity for doing longer duration global simulations at a relatively lower cost. So with that, I'll say thank you and open for any questions if I haven't spent too long talking. That was me.
So this fast emergence of this rainfall overestimation, which we've seen in almost every model that has been presented in the last couple of days, right? Is that an opportunity to design cheap, I don't dare calling them cheap, but cheap experiments to try and figure out what's going on, do you think?
Yeah, I think the results here show that there's opportunity there. I think maybe we have to have some careful thought about how we design those and what tests we want to run. It's still not cheap, right? Relatively cheap, but I think that's a good kind of suggestion for future work, for sure. Okay. You want to use this mic?
So getting back to your original sort of motivation, which was to see, does this matter? Or would you just continue to use the limited area setup? What do you think the conclusions of that are?
I think that's kind of a cruel question, given I put on the limitations that we maybe want some more model runs before we start to make real strict conclusions. But I think what I would say is we're probably yet to see the evidence to say that we're providing significant improvements by simulating across the full tropical channel. But I think there's more work to be done to show that, and then by running more cases, we might still see that. Is that enough of a non-answer?
All right, don't hate me, everybody. So this plot is perfect. So in the Atlantic, you're showing too much precipitation, and this is just a comment. I was in a field campaign in Cape Verde just several weeks ago, and one of the problems we wanted to tackle was ITCC convection, and day after day, every model was putting in beautiful ITCC there. Day after day, there was no ITCC. Mm-hmm. So I think this is probably like a common problem of global models, especially in the Atlantic and near Africa. I'm not sure why, but the models tend to be too aggressive at putting an ITCC there, but in reality, it doesn't rain as much.
Yeah. I think, yeah, good comment. And I think it's certainly true of other models than what I've shown here. And you also see it in longer duration simulations, climate simulations, rather than just short duration simulations that I've shown here.
little unclear whether this next 20 minutes is a constructive or a disruptive part of the conference, but we'll find out. I hope it's constructive. So the idea here is simply for each of the groups to quickly give us some 1 or 2 highlights of what's happening so that other groups may adjust their discussions or not or otherwise. So it's really just for us to, and also if there are some topics that people feel I wouldn't call them lowlights, but where they're struggling a little, it would also be good to know for the other groups and just to see where we are. So does anybody want to go first? There's no agenda here. It's just really each group maybe come up 5 minutes or less and just tell us where you are. There's Pierluigi sits right in front ready with his computer, so we'll start with him.
Right. So we decided to sort of take it in a systematic way through the scientific challenges. So we had a lot of talk about process fidelity, and so this scientific curiosity and pursuing the understanding of processes versus then demonstrable benefits to society, which should actually eventually work together, but possibly not from day one. So maybe there are different phases there of sort of development, understanding, and benefit to society at a later stage. But within that, there was a bit of a tension between, again, this idea of process fidelity and then affordability of things. And it's not completely clear that if we achieve process fidelity, this will translate into an immediate benefit for society. And there was a very nice example about being able to resolve eddies in the ocean, and they look fantastic and all that, but when you take their statistics, they're terrible. So if you were then to use that in a global model to be used long-term, it might have a deleterious effect, which was basically the same problem we had in Primavera. So there's that, and then there is still the inherent challenge that even if we go to these scales, we'll always have subgrid and missing processes. And so where do we find that balance? And then there's a whole issue of how to initialize such systems. So we need, for example, coupled and efficient data simulation, and the current data simulation systems, so 4D-VAR, for example, are very likely not suitable for this. And then connected to that, there is also the spin-up problem. So some of these systems may require very long spin-ups, and we need technology for that. Otherwise, all our beautiful process capability ends up being wasted by the fact that we can't initialize the system. And then there is the entire issue of boundary conditions, and Martin talked a lot about that, and some of them are difficult to observe. And the examples were what Martin said, the soil physical characteristics, but also we were talking with Nikolai, so bathymetry in many parts of the world, we don't, it looks like something that should be doable, but we don't know the bathymetry at those scales. And then we talked quite a bit yesterday and today about the scale interactions and long-term upscale effects. And this comes down to this whole notion of how to best combine global and regional models. So ideally, we should be able to find criteria that would say, okay, these problems you treat with a global model at 1 kilometer, and these problems we treat with a regional model. And where can you use the regional models to develop things like parameterizations, numerical schemes, and all that are then usable in global models. But also, where can you demonstrate that these small-scale effects do change the climate trajectory? So, and we talked about that a lot in our past meetings. Yeah, and then remembering what Kathy said, as we go to 1 kilometer and we strive for process fidelity, we disable certain mixing parameterizations, basically. And we lose our knobs, and then we have this challenge of tuning without those, and the challenge of tuning with models that are very, very expensive. So some ideas, can we test certain things in isolation? And it goes back to the coupling problem. Can we test and assess in very particular regions and over very particular time periods that are data rich and allow us to come to conclusions that are very physically based and should then translate, and we do need to test that, but should then translate So we focus our resources on well-observed, well-constrained systems, and then we try to generalize to the planet. We also did talk about, and this goes later on the actions, engaging with observational programs that are suitable, and the examples is the Earth Care program, and then also this program in Germany, HDCP squared, where they are really strongly interacting with observations, and they have observations over the range of scales that are relevant to this activity. And the other question is, and that's quite a challenge, say that we now can demonstrate benefits, and this was similar in the quarter degree world. Say we can demonstrate the benefit of going to this resolution. Is it really a robust result? Can it be transferred? So we have a handful of models that demonstrate improvements. Can we then say to the rest of the models, look, if you go here, you'll have the same results? And it's not clear that is something we know how to do and that we have enough evidence for. So this transferability of scientific outcomes, is it robust enough? And how can we design experiments that allow us to do that? I can skip this. Component models. We possibly agreed with Martin that land is one of the places that needs most attention, particularly because of things of the landscape that start to pop out, like water surfaces, all sorts of water surfaces, but also because of what he said about human interactions. I think there was more confidence about the ocean, apart from the whole issue of mixed layer parameterizations and the issue of coastal problems, and it's not clear to us whether coastal problems need to be part of the coupled system or can be treated as a, so this we'll discuss more in the next few days, can be treated as a sort of accessory module. And then, yes, this mismatch between complexity and resolution is similar to this upscale, downscale divide. Which bits do we really need to run coupled, and which bits can we afford to run on the side? In terms of coupling, we did identify the fact that we have inconsistent, disparate methods and approaches and philosophies, and an example is this idea of coupling at exactly the same scale, with basically without interpolation, or even having the same mesh without interpolation, versus using all sorts of higher resolution in this component, no higher resolution in the other component, that's interpolate and lose mass and not conserve anything as we do that. So it's quite ad hoc how it's done. So that maybe needs to be looked at as we're going to put more and more money into this. And yes, there are all sorts of examples of things that are not coupled, and the coastal came up. But also, one thing I wanted to mention today to Martin, so when we talk about flooding, this bit about the terrestrial versus oceanic source of flooding, but also the interaction of the wind with these systems, because a lot of these systems that are embedded in land surface models just function with gravity. There is no wind. And there was an example of the Potomac being completely emptied in 2018 by just a little bit of wind, and water was pushed upstream completely. So there are some examples. I have a list of things that should be coupled if we go to those scales. Yeah, well, the tuning, I don't know what to say about the tuning. Yeah, I think this is about the core of the things that we really discussed thoroughly, and then the other ones we rushed through. We've done everything, but I would say the other ones are still quite green, and maybe it's best that I stop here. Feel free to add if I made a very personal selection of things. Just raise your hand and say, "Oh, but you should have said." Oh, okay.
Any questions? Any? Kath has a question for you.
That's already on our list. It's said you need to engage, you need to bring your also we need prominent example now is Earth Care. German program. goes back to this idea that we may have regions and or time periods in which we have suitable observations, and then we do a lot there, and then maybe bring that to the global.
Okay. Oh. Okay. Ooh. Careful. Who wants to go next? You want to go next? You and Rosie. Who's your summarizer? The official summarizer. That's all right. Quick is good. People want brownies. Andrew was defending the brownies outside with his life.
Yes, well, that's probably the place to start. So I'm here with Rosemary to represent Group 1. We sit just upstairs on the first floor. If you want to come and join us, if it sounds fun, then you're more than welcome. We've still got another 3 and a bit hours to go, so transfer is very welcome. We stop early, so we started the run on the brownies this afternoon. Sorry, but not sorry. So we take good breaks, and we're a great group spanning across various dimensions. What we don't really have is observation people, so we flagged that this afternoon, that we're a meeting of modelers talking about modelling. What we did on day 1 was get to know each other, and unlike the previous group, decided which questions we weren't going to address. So I'm afraid we might have some blank bits in our answer sheet, but what we are doing is answering the questions that we want to answer very well. So this afternoon we jumped into the evaluation methods and talked a fair bit about how we might go about evaluating K-scale models. In practice, what I think we're doing is developing a kind of experimental design, and we've been kind of pushing that, stress testing a little bit. What are the options? What are the constraints on what we're going to do? So I think give us a bit more time and we'll be able to present some thoughts on an experimental design, and we're quite excited by the prizes. And we can probably leave it there. I guess one of the things that came through this afternoon, as well, just for reflection, is the extent to which a lot of the kind of protocols and, if you like, some of the infrastructure that we think we will need to do a decent job of intercomparison already exist. So I think there's quite a strong appetite not to go reinventing things, but to really, feel free that we'll pick the best bits from the efforts that have gone on. But we sit upstairs, everyone's very welcome, and we take good breaks. Thanks.
Any questions, comments before he runs away to the brownies again? Yeah, absolutely.
I guess a thought-provoking question that came up yesterday was, why are we all using different models? Why not centralize our efforts and use one model and do it well with one model? Of course, the logistics of it are very hard, right? Like, how do you choose which model? And there are many other logistics, but that was a very interesting question that was brought up yesterday.
Yeah, I like at least being provocative about that one, because I mean in Europe it's 2 models. That's probably okay, but in the US it's already what, 6, something like that. Then all sorts of different. So that requires some thought. The other one I was inspired to ask, and that might go to all groups. What is the equivalent of the single column model? And I'm only asking this. What's the cheapest modeling setup that we can use to test certain aspects of these models? I think that's going to be really hard, but I think we really need it. And you were saying modeling hierarchy. Yeah.
It's still a model, but I can add one thing, and this goes back to the conversations we've had. We're trying to set it up so you can have on-off switches.
Okay.
All the atmosphere, that's great.
Aaron has his hand up too.
I missed an opportunity to bring this up during my talk, but there was a figure where I talked about the single model, right? I think that replaces single column.
Yeah. Yes. And the beauty is it has to be the idealized model, but with the same, ideally, everything, right? Same physics, same dynamical core, and so on and so forth. And that's what makes it challenging, because some of those models are not built to have that, and some are. And so it's going to be pretty interesting. Okay, anything else on that one? If not, we hand over to Fanglin and Nicolina. I don't know who the rapporteur is today. Fanglin, yeah?
Good discussions. We didn't follow like one by one. We just let everyone speak freely what come to their mind, and we try to capture. Sometimes focus the discussion to one particular topic. Well, the first question may be, Christine, and for you, why it's called K scale, not KM scale? That's the first. We took quite a few minutes to discuss that. So, do you have an answer why it's called K scale, not K? So the first question I think is very interesting. I have a list, but I want to touch everyone. So seems we should decide on different types of high resolution modeling, depending on the science question to be answered. Not just everyone goes to say 1 kilometer or 3 kilometer. There's reason behind it, because like for some of the climate simulations, you need to run like 400 years to get really understand the climate variability. You really cannot afford to run 3 kilometer at that resolution. There's also suggestions say you do not always need to run coupled model. You can have some of the science question answered by running a composite model, and not only answers only spatial answer only model. So a question for the composite model, since no one talk about the chemistry and the carbon cycle, or also chemistry carbon cycle, or this K scale community, should we consider this or not? Another question, like we have always talking about the horizontal resolution. Is the vertical resolution also you have to change it at certain scale? So if you are running horizontal, 250 meter vertical should be 10 meter or even higher. Also, the PPL scheme may not be working anymore. The current the turbulence scheme, you need to have a new approach, and the bulk, especially for the bulk flux formation. Of course, with not-to-not process should be included after this morning's preliminary presentation. For evaluation, we have very good discussions and topic touch a lot of areas. One thing is in the NWP world, we have a so-called scorecard. Should there a scorecard for climate model as well. If you want to participate in the climate, the K-scale evaluation or in the comparison, you should maybe have at first pass a certain standard scorecard to get into the gate. Also, evaluation part should be aggregated to a common resolution. At least we have observation to support. Otherwise, you should have a benchmark to compare. Otherwise, you can say, I have a model, it's running. The high resolution is actually doing anything good or not. Or have the benchmark at the standard resolution to answer the question. Also, a question asked how to better use satellite observations, reach satellite observations, how to make best use of them. Some of the next step, say, since we cannot afford to run a very high resolution model for long time, maybe the K-scale model can really be used to understand the predictability at the sub-signal time scale. That's a good area for application. Also to understand when and where for two-way coupling. Like examples of hydro part, most has been run in one-way coupling. Should run two-way coupling at what time scale and spatial scale. Also, some suggestions instead of only checking the climate statistics, also check the weather phenomena. Like one picture I showed, the Ohm core, the Florence, the storm structure, vertical structure, probably should be checked in the high resolution climate model run as well. There are many other things. One challenge is how to share the data, especially share data with universities. The professors nowadays cannot run the K-scale model. They don't have the resources, but they can definitely contribute to the science. And so since cloud part is not a good way to store the data because you have to pay to download for downloading the data. So there are any, but we need to think other ways to share the data, or use common data structure, or also mention the data compression. I think I stop there.
Any additions, any questions for Fang Lin? All right, so looks like everybody is making good progress through the questions. Sounds like everybody's having fun. Okay, no one's contradicting me, so that's good. So the final question before brownie time, and I promise Andrew won't be standing there as you get out there. Do we want to have this half hour again tomorrow, or would you rather have that time for keeping going on your discussions? Any views on this? Quick little updates. Okay. And I'm going to throw in another challenge for the groups to think about, and that is I'm really worried about the divergence of the CMIP-style climate modeling efforts from this, and so much so that there are shouting matches across the divide that are frequently taking place. And so if we could think through how would one use these high-resolution models to inform, help, support, understand the coarser resolution models, which whether you believe it or not, will be around for another 2 decades, as a minimum, is my prediction. So if we could make some scientific connection, maybe the shouting stops if the scientific connection can be made. So that would be really helpful if people had ideas how to do that. I think looking at weather scales is a really nice connection because, you know, how I would assume that in these high resolution models, the weather scales are so much better than they are in low resolution models, but that's just an assumption. Maybe that's a nice scale that connects the two because, you know, weather scales are in lower resolution models as well. They may just not be as well represented. So there could be a nice activity where we say, let's meet at the weather scale. Let's meet at the scale of extratropical cyclones. And, you know, we can't meet at tropical cyclone scale. We already know what's going to happen. But at extratropical cyclone scale, there's probably a nice connection we can make. Just wanted to throw that in because it bugs me. It bugs me. There's too much shouting and not enough trying to work together. All right, with that, it's brownie time, back at 4. Thank you, everybody, for your enthusiasm. It's much needed. And you know, people didn't shout. But we're not here to make news. That's not our job. Excellent. No, I know. That's the problem. Right. The respect. Right. Yeah. There's a lot of that going around.
12 minutes plus 3 minutes for questions. To the speaker, I will give a 2-minute warning before the end. And we start right away with the first talk by Rosima Berrios about aquaplanet simulation of convectly coupled equatorial waves with MPAS.
Okay. Hi, everyone, and thank you to the organizers for the opportunity to give this talk. My name is Rosima Berrios. I'm a scientist here at NCAR, and I work primarily with aquaplanet simulations using MPAS, and that's what I'm going to tell you about today. My efforts focus on the tropics for various reasons, and one of the reasons is beautifully summarized with this quote from Moncrief et al. 2012, in which they said, "We have difficulties with reliable representations of tropical convection in our models, partly because of the complex hierarchy of interacting scales, processes, and phenomena." And of course, we can provide you a very long list of challenges when it comes to representing tropical convection in the models, but I'm just highlighting a few here, and they are intentionally chosen to represent the different scales of the tropical atmosphere, going from the double ITCC problem, that's a global phenomenon, down to the synoptic and planetary scale disturbances as represented by equatorial waves. But if we continue down the spatial scales and temporal scales, we also have a lot of challenges when it comes to mesoscale convective organization and even rainfall extremes. So today I'm going to be focusing on the second bullet on the left, which is a poor representation of equatorial waves and the Madden-Julian oscillation. Here's an example showing that challenge. So on the left, we have a proxy for observations, which is CMORPH. And on the middle and right, we have the GFS and IFS 5-day forecast. And what you're looking at is a Hofmüller diagram with time decreasing along the y-axis and longitude in the x-axis. And in the observations, we see a lot of variability. So there is subseasonal variability, but most importantly, there is zonally propagating features. Those are the equatorial waves. But when you go to the global models, they pretty much have stationary features and not so much zonal propagation. Of course, this is a study from 2018. Both centers have made substantial improvements to the models, but this issue keeps coming up with operational as well as GCM models. So in light of the theme of this conference, the motivation here for my work is, can kilometer scale models alleviate some of the modeling issues regarding tropical rainfall? And getting more from a phenomenological perspective, we're interested in knowing whether or what is the sensitivity of tropical waves and their structure to resolve versus parameterized deep convection. So the way I'm approaching these questions is with modeling experiments using MPAS, or our model for prediction across scales, atmosphere. I'm going to primarily focus on aquaplanet simulations, but if I have time, I'll show you a couple of examples from our diamond simulations as well. And I'm analyzing these simulations by looking at a comparison of equatorial waves with resolved or parameterized convection, where the resolved experiments are our kilometer scale experiment. So I believe I'm the first to talk about aquaplanet simulations. So in case you're not familiar with them, I want to give you a brief overview of what aquaplanet simulations are like. So we're using the model for prediction across scales. It's a global model here at NCAR, and amongst the benefits, it has a grid refinement capability, which allows us to have convection permitting resolution or high resolution in one part of the globe, seamlessly transitioning to coarser resolution elsewhere. And the framework I'm using is an Earth-like aquaplanet. So like the model, like the name says, it's like Earth, but we have removed the land, the sea ice, and the seasons. And we keep some components that are very important, such as the diurnal cycle, rotation, and meridional SST gradients. So the SST imposed here is zonally symmetric. It stays constant throughout the simulation, but we only impose the initial conditions. We let the model freely run. And importantly, in this work, we're using model physics from the numerical weather prediction community. Traditionally, aquaplanet simulations are run with GCMs, and they use physics designed for climate applications. Here, we're using model physics designed for weather applications. And in particular, I want to draw your attention to the last physics scheme, which we're using a scale-aware Tiedtke cumulus scheme, even when we use the convection per meter resolution. So my approach here to address the question about the sensitivity to horizontal resolution and to kilometer scale resolution in particular is to have a hierarchy of experiments. So I use the same model, same vertical grid, and same model physics, but I only vary the horizontal grid spacing. The experiments are designed such that the 120 kilometer cell spacing is meant to mimic what our GCMs or climate models used. The 30 kilometer cell spacing experiment is meant to mimic our high resolution climate models. 15 kilometer cell spacing experiment mimics our operational global models. And the last one, which is the most exciting but also the more expensive one, is our 3 kilometer cell spacing experiment, which it's only using 3 kilometer grid spacing in the tropics, and I'll explain that a little bit more in the next slide, transitioning to 15 kilometer elsewhere. So the first three simulations, the 120, 30 kilometer, and 15 kilometers, all use convection parameterization everywhere at all times. They are also 3-year-long simulations. The last one, the 3 kilometer experiment, it's only 160 days long because that's as far as we could get. So the analysis is just going to be based on the last 100 simulation days of all the experiments. So here's what that aquaplanet simulation looks like when we use the kilometer scale. Like I mentioned, I'm using the grid refinement capability of MPAS. So as noted on the right, the tropics, or more or less from 20 south to 20 north, we have 3 kilometer grid spacing and explicitly resolved convection. And then forward of 20 south and 20 north, we transition to 15 kilometer cell spacing and a fully active convection scheme. And the animation you're looking at is showing precipitable water vapor from that 3 kilometer experiment for a 20-day period. And it's meant to show all the rich phenomena that we can get from this very idealized experiment. You can see that the red colors, which are the moisture-rich regions, are in the tropics as we expect them. And depending on where your eyes are drawn, you may be seeing all the interactions that go on between the tropics and the mid-latitudes. Or you may be even seeing some zonally propagating waves with the naked eye. So pretty cool. So let's use now this animation or this simulation. I like to use them as a statistical database that I can then sample with statistics to understand what's going on in the model. And in doing so, we find that the kilometer scale simulation captures more tropical rainfall variability. And we can see that here, this is a plot showing the total variance of tropical rainfall between 10 south and 10 north. And the 4 different experiments are labeled on the bottom. It's pretty striking to us that even though we have 3 simulations with very different grid spacing, so 120 all the way to 15 kilometers, they are very, very similar. But then you get almost a step function when you go down to kilometer scale, where you have twice as much rainfall variability in the tropics in compared to the other experiments. So this is telling us that there's a lot more variability, a lot more of that subseasonal variability within the model. And we can partition that rainfall into different phenomena, the equatorial waves, and this is what I'm showing now. So we're looking at something similar, so rainfall variance, but now it is filtered for different tropical disturbances. The light gray is Kelvin waves, which are eastward propagating, and then the other 2 advective disturbances and inertial gravity waves are westward propagating disturbances. And so regardless of the wave, we do see larger variance when we go down to kilometer scale resolution. And the difference between the 3 kilometer and the rest of the experiments becomes larger when we look at the finer scale or the smaller scale disturbances, such as the advective disturbances and the inertial gravity waves. But an important point here is that all of the simulations do capture the waves, so then we can go into the model, go and find those waves, and take a look at what their structure looks like. And so when we do that, we find that kilometer scale simulation captures stronger equatorial waves. We can see that in these plots. So we're looking at rainfall rate anomaly. The anomaly is taken with respect to the zonal and planetary mean, to the zonal and time mean. On the x-axis, you see wave phase. That's a way to normalize time and space. So just all you have to think about is wave phase 5 is the convective peak of the wave, and wave phase 1 is then the convectively inactive phase of the wave. So we have 3 panels. On the left, there are Kelvin waves. On the middle are inertial gravity waves, and on the right are Easterly waves. And then the 3 different colors represent the different experiments. The 3 kilometer, which is the purple line, it stands out again from the rest. So not only does that experiment produces a stronger rainfall anomaly at the peak, but there is also a more negative anomaly at the convectively inactive phase, which means that not only are the waves stronger at their peak, but also that transition from convection to dry conditions is happening a lot faster or steeper in the kilometer scale simulation. So we looked into various reasons. We looked at the different vertical structures of this wave, and we found something very, very noteworthy, and that is that these experiments have different heating profiles, especially near and below the melting level. So here is a plot that shows that. This is the vertical profile. So we have pressure on the y-axis, and what it's plotted is the so-called Q1, which is a proxy for diabatic heating. The black lines show 2 sources of observations, and the other colored lines are the different experiments. And what I'd like to draw your attention is to this region just below the melting level, where we have a very steep gradient, very sharp gradient in the experiments with parameterized convection, which also appears for the other different waves. And we believe this is, has to do with issues with the parameterized melting in the convection scheme that we're using. But importantly, because the surface rainfall is proportional to the vertical integral of this quantity, we believe that this discontinuity below the melting level is partly responsible for why the waves are less variable and also weaker with parameterized convection. I'm running out of time, so I'll just tell you very quickly that these results are also true for real data simulations. You're familiar with the Diamond Initiative. So our institution, led by Falco Jude, contributed a global simulation with 3.75 kilometers to the Diamond Initiative, but he also performed what he calls a resolution ensemble, in which he redid the same simulation for 40 days, except using different horizontal grid spacings. I'll focus again on the same 3 different grid spacings that I showed before, but here is a similar plot showing the rainfall rate anomaly as a function of wave phase. And once again, the 3 kilometer experiment stands out from the rest in being the one that shows the strongest waves, but it's also scarily similar to the observations. I promise I double checked this. There's no code error or anything. It really, the 3.75 kilometer simulation happens to be the closest to the IMERC product, which we're using as a proxy for observations. And I'll just skip through these very quickly just to show you the vertical profiles of Q1 and just also show that in this observed or real data simulation, we also see that sharp discontinuity in the 15 and 30 kilometer simulations. So just to conclude, we're after these 2 questions, and I'm looking at them from a hierarchy of simulations. The bottom line here is that kilometer scale simulations captures more tropical rainfall variability, stronger equatorial waves, and more accurate vertical structure. We have a hypothesis for why that might be there, but even though the aquaplanet simulations don't have a truth, so we cannot say that the kilometer scale simulation is the closest to reality, at least the Diamond simulations provide some proof that indeed that simulation is the closest to reality. I'll stop there. Thank you.
Thank you. So we have time for 1 or 2 questions. Are there any questions? Yes, just please use the mic.
So thanks, it was really interesting. And there was a big jump between 15 kilometer and 3 kilometers. And in the 15 kilometer, is it the cumulus parameterization making the precipitation, basically?
Yeah.
Have you ever tried turning off the scheme at the coarser resolutions?
I have, and it becomes very weird. Like,
Weird.
yeah. I mean, very weird in the sense that you get these very linear features and the convection looks very clumpy, and at least at 15 kilometers, I don't know if it's fair to do an experiment where at 15 kilometers you have no convection parameterization. It just looked very unrealistic.
What if you do it the other way? You make the cumulus scheme active in 3 kilometers.
So Falco did that experiment. He calls it an accidental experiment because it was an accident that the convection scheme was on at 3.75 kilometers. And the simulation looks a lot more like the 15 and 30 kilometers.
Yeah, I have to confess that I saw that figure yesterday.
Okay.
Okay, and thank you very much. We move to another region, so now we go to the cold climate, and we go to the Arctic with a speaker, which is the talk by Mark Seefeld.
Nothing like switching from the tropics to the Arctic in one presentation. All right, so I'm here to talk about process resolving fully coupled Arctic climate modeling and prediction simulations. To look at this, I want to first get into the motivation behind this. Why are we trying to get these higher resolution simulations? So to start with Arctic amplification, we have an Arctic surface has warmed twice as fast as the global average, and this is referred as Arctic amplification. There's a recent study by Taylor et al. 2022 that does a great job in summarizing Arctic amplification. And here we can see this tremendously larger temperature trend in the polar regions, especially for the Arctic, than we have in all the regions. This rapid Arctic surface warming is resulting in dramatic changes to the Arctic climate system, including sea ice loss, reduced snow cover, degrading permafrost, impacts to the ecosystems. And this is a coupled atmosphere, land, ocean, sea ice process, so the modeling that we're applying to it is all in a coupled sense. To continue the motivation, despite the significance of Arctic amplification, climate change and the Arctic climate projections continue to have the largest amount of uncertainty. So here again from Taylor et al. 2022, we have a plot of temperature trends by latitude and looking at the CMIP6 models. And while we have a range here of about 0.3 to 0.4 Kelvin, in the Arctic, we have a range of around 1 to 2 Kelvin across the simulations. So there's a large amount of uncertainty with this, and we believe that an improved representation of the local processes in the Arctic is necessary in order to reduce this uncertainty. These local processes that we're dealing with, focusing on the sea ice and the sea ice decline, the largest variation to go with the variations in the temperature trends relates to the sea ice, and there are local processes that are involved in how the sea ice forms and degrades. We can also have a focus on increase in oceanic heat transport into the Arctic, and that influences Arctic amplification. And the results that I'll be showing will highlight this aspect of looking at how the depiction of the ocean circulation changes with improved resolution. Then we're also getting a small scale structure of the atmosphere. This plays a role in clouds, turbulent fluxes, and the surface energy budget. So I'm a part of the group called the HILAT-RASM project. HILAT is the High Latitude Application and Testing of Earth System Models. This is a science focus area from the Department of Energy. And this is then in collaboration with the Regional Arctic System Model, which has been around for about 15 years between University of Washington, University of Colorado, and Naval Postgraduate School. And we're applying both global and regional modeling, analysis of capabilities to address these polar processes and their impacts. And this is our new hot graphic that we have to show the coming areas that we're looking at with the next round. So with this, we're looking at, again, with global and regional modeling tools. The global tool we're using is the Earth Exascale Energy System Model with a regionally refined resolution for the Arctic and subarctic. Hereafter, I'll be calling this E3SM Arctic. So it's a global ESM, capabilities, a variety of configurations, fully coupled, data components, slab ocean, nudging, cloud locking, and so forth. The regional model is the regional Arctic system model. So it's a regional Earth system model where they focus on the Arctic Ocean, cryosphere, hydrology, biogeochemistry. Then we also have a variety of configurations with this. So now we're going to go through these different models, where we're at, and some results from both of them. So the E3SM Arctic is our regionally refined model, or RRM, of E3SM with a focus on the Arctic subarctic. And we have independent ocean sea ice and atmosphere land regionally refined meshes. So for our ocean sea ice mesh, it starts off at 30 to 60 kilometers in the southern hemisphere, and then it's revised around 30 kilometers in the tropics, and then it slowly gets to 10 kilometers in the Arctic and subarctic. One of the key areas as these meshes are being defined that we have to pay attention to is the ability that we are getting the ocean transport areas open and fully resolved. Typically, this requires multiple grid points, so we're not basically getting sea ice jamming up and so forth. And to illustrate this, we have this strait here between Greenland and Ellesmere Land, and we have then these grid points there that have that strait open. So this is an example of showing the E3SM Arctic in a ocean sea ice mode. So this is using the ocean sea ice regionally refined mesh. And on the left side, we have the results from the E3SM Arctic. And on the right side, we have the low resolution E3SM model. And we can see then that we have an improvement in stratification and representation of coastal currents. In particular, highlighting, this is the Barents Sea opening. This is going from Svalbard to Norway. And so on the coast here, we have a much, much better representation of the Norwegian coastal current. And this is then transporting in warm water into the Arctic that is not being fully captured in the low resolution simulation. And so this is a key important factor to get right to represent fluxes of volume, heat, and fresh water into the Arctic for the changing Arctic climate. Next up, we have the atmosphere land mesh for the E3SM. And so this is varying between 1 degree elsewhere, and then it goes down to 0.25 degrees in the Pan-Arctic region. And this was developed to basically focus on capturing the storm tracks into and out of the Arctic. So where are we going from that? That simulation has just been getting going, so I don't have any good fancy results on that one. But so where we're going in the future with this is we want to continue to explore the E3SM Arctic capabilities, focusing on the polar representational model physics, and looking at higher resolutions. So with the ocean sea ice mesh, we're exploring MPAS Ocean, which is the ocean model in E3SM, that goes down to 2 to 3 kilometers resolution in the Arctic. And then for the atmosphere land, looking at an 1/8 degree resolution in the Arctic, and that could be in a regional sense. So just looking at, let's say, the North Pacific storm track, if we want to focus on that, so it's not chewing up all the computing capacity to go the full Pant-Arctic region. So next up is the regional model, RASM. The regional Arctic system model is a limited area, fully coupled atmosphere, land, ocean, sea ice model focused on climate simulations of the Arctic. For RASM, we have the atmosphere is handled by WRF, sea ice is handled by SICE, ocean by a modified version of POP, land is using the VIC model, and we have our streamflow routing called RVIC, and all this goes through the CPL7 coupler with a similar framework to that of CSM. The different partners with the RASM project, University of Colorado, we handle the atmosphere with WRF. University of Washington takes care of the land and streamflow. The Naval Postgraduate School handles the ocean and sea ice. So our focus with RASM is understanding mesoscale processes and their feedbacks, critical representing the Arctic. So it's a dynamical downscaling of reanalyses as well as ESMs. I'll be submitting a paper soon that we use RASM to downscale simulations from the decadal prediction large ensemble project. Then we're also optimizing the experiments with varying parameter in space, and then with any force model like this, we can verify against observations in space and time. Our primary simulations and deal with an ocean sea ice at 9 kilometer or 1/12 a degree, the atmosphere land at 50 kilometer, then also ocean and sea ice simulations at that 1/12 a degree, and then also ocean sea ice at 2 kilometers, which are the results I'll be showing here in a second. The planned RASM simulations step up those resolutions, looking at decadal simulations with ocean sea ice at 2 kilometer, atmosphere land 25 kilometer, then fully coupled annual simulations with the amount of computing power looking at the ocean sea ice at 2 kilometer, atmosphere land at 10 kilometer. And again, the results here are now going to focus on this ocean sea ice simulation at 2 kilometers or 1/48 a degree. So here we're showing the 10-year mean temperature and velocity at Fromm Strait, which is between Svalbard and Greenland. And we got 4 different representations here. The upper left is the fully coupled 9-kilometer ocean. The upper right is the 9-kilometer, and with 60 vertical levels. The lower left is the 2-kilometer with 45 vertical levels, and the lower right is the 2-kilometer with 60 vertical levels. And so with this 2-kilometer and 60 levels, one thing to point out here in that it was brought up the other day where we always talk about resolution in the horizontal, but this is also showing a large bang for the dollar, and going with 60 vertical resolutions shows a much more defined coastal current here than what we were seeing in the 9-kilometer and with the 45 vertical levels. Then we got the RASM ocean at 2 kilometers looking at eddy kinetic energy from the top 220 meters for the Fromm Strait region. And this again is showing the 2-kilometer has a much significant more capturing of the eddy kinetic energy. And this results in an increased role of eddies, horizontal and vertical, including air-sea exchanges at the higher resolution that is being better captured with these 2-kilometer simulations than what we were seeing elsewhere. So RASM in the future, we're going to be replacing VIC with the Community Terrestrial Systems model for the land. We're going to be upgrading WRF to 4.4 to leverage recent developments, as well as improved capabilities for future upgrades. And then we're also looking at running standalone WRF simulations, but getting our lower boundary conditions from the ocean sea ice simulations from RASM, so we're able to get more experimentation capabilities with reduced computational cost. And that is all.
Thank you very much. There is time for questions. Christian?
Not to.
You have the floor.
I'm puzzled by this huge discrepancy between the atmospheric resolution and ocean resolution working so well by the looks of it. You know, you have the atmosphere forcing the ocean at 50 kilometers, and then you get all that small-scale variability. Does the atmosphere not matter? The small-scale stuff in the atmosphere doesn't seem to matter so much. Or what's going on?
That, unfortunately, is outside of my my atmospheric understanding as well. So I'm going to have to pass on that one.
It's quite phenomenal.
Yeah, and I will say those 4 cases are with data atmosphere, so actually showing like less resolution than what we're seeing with the fully coupled models that you're talking about, the 50-kilometer.
Nikolai.
From our experience of running high-resolution Arctic, we tried to run it with 2-kilometer resolution, and we didn't really get well representation of eddies. So, and we only get them at 1 kilometer. Did you look at your 2-kilometer resolution runs in terms of like eddying ocean? So do you have eddies basically well represented?
Yes.
Or you think you have?
I think we have them. They're all represented, yes.
Okay. So they are forming along the coastal currents and stuff?
Yeah.
Okay, cool.
Yeah.
Thanks.
Maybe I will ask one question, because you started the talk motivating it with the Arctic amplification.
Yeah.
And I'm not an ice person, so are leads important for Arctic amplification?
Yes. So that gets into the variability with the sea ice and the variability the sea ice has in the results in Arctic amplification. When I talked about the small scale processes that's key to getting the sea ice right. It gets into things such as leads and melt ponds.
Do you know how much of a difference it makes? So if you would compare with and without leads, is it?
I do not know how much of a difference it makes with that. No, I do not.
Any last question? No? Then thanks again for the talk. We stay in the north, in Alaska, and the next talk is by Andrew Newman. On the left, sorry.
It's almost like we coordinated these talks. I'm happy with Christian and Andy and Andrew and working with us to get an order that makes a lot of sense. So I'm actually going to be talking about an application of the RASM model, but I'm not going to really show any results. I'm going to talk about the process to get to hydrometeorology and terrestrial hydrology across Alaska. So I kind of changed my talk, and I'm going to focus more on the knowledge co-production angle. There we go. In the process of defining our model configuration and the simulation set that we're trying to develop. So this is a fairly large interdisciplinary project. It's funded by the NSF Navigating the New Arctic program. This is kind of the Arctic Rivers project. The authors here are more specific to the work that I'll be showing, but also there's a lot of input from the whole research team, which is listed here. And I will say we also work with Mark and John Casano a lot and have interface with Bart Nyssen at the University of Washington, just kind of land modeling and RASM modeling generally. And so this is, I think, a really exciting project to me. It's been very eye-opening, and so I wanted to kind of share that perspective with everybody. So the main motivation of this project was kind of what Mark showed. There's a lot going on in the Arctic, right? There's this Arctic amplification problem, and there's a lot of change happening very quickly to ecosystems, but also the human system. And so we had some underlying connections to folks in Alaska that we leveraged from the project outset, and we really wanted to deal with this idea of knowledge co-production where you blend different viewpoints, blend different knowledge bases into trying to develop a further understanding or a more complete understanding of a problem, right? That's kind of the generic definition of co-production. We were focusing on our expertise, so atmospheric, regional hydrology, snow physics, things like that, and what our connections were in Alaska. So we're working in this kind of Yukon River basin up to the Arctic Ocean, and we really wanted to focus on how we connect indigenous knowledge, our Western perspective, Western agencies, and thinking about how this is going to impact communities that are reliant on fish habitat and river ice transport. How is that going to change in the future? And so as we all kind of know, climate models and then subsequent projection simulations require a lot of technical decisions. So I just kind of have a lot of things listed here. But the key point is in the lower left corner where all of these decisions that we make along the chain of how we define what model we're going to use, is it going to be dynamic, is it going to be statistical, to get to our impact modeling, all affects the usefulness of the model. You know, does it actually represent the things we want to have it represent? And this impacts how it should be used for, you know, decision support and climate adaptation. You know, this is still a very open area, and it's really interesting to me to think about, you know, all of the choices we make as far as the representational usefulness of our models, and are we doing things that maybe we shouldn't be doing if we're not careful? And even here, I'm sure there's things that we're doing that we shouldn't be doing, but maybe we're trying to be a little bit careful. And so as far as our model system design, and this really goes back to proposal design of the project, from the outset, the process was to use people that we know and find other connections to really try and understand what a legitimate problem is, like an application, and work science questions out with that in mind. And so we worked with the Yukon River Intertribal Watershed Council, which is kind of this nonprofit organization that represents, I think, almost every tribe or First Nation along the Yukon River watershed. We worked with some of their executive board, their science lead, to kind of define some of our initial research questions. And then throughout the project life, now that it actually was funded, we have webinars, community webinars, we have community engagement, we have an Indigenous Advisory Council to kind of center what types of questions we may want to deal with, if we need to change tact on how we're designing experiments, et cetera, how are we going to make the information also usable. So like things like output, the technical issues of like how you disseminate data. And so some of the questions I kind of talked about already, fish habitat, river ice transportation. But how will these communities that are reliant on these things for way of life, subsistence, fishing, economic issues, just cultural, they're really their being. How are they going to be impacted by all these changes, right, that are going to impact fish habitat? So air temperature, permafrost, precip, groundwater, stream flow, river temperatures. So you might think you need reasonable historical representations of all of that. You also need what you might try to define as reasonable change signals of those things, right? And that is the difficult question that I'm trying to deal with on a lot of different projects right now, is how do you assess these models in a historical sense for actually trusting the change signal, right? It's a really tough question. And so what we're trying to do is use these questions to then, and the needs of communities to then try to define a modeling system that we think is at least a step in that direction. And so what we are kind of leaning towards, which is why I'm talking here, is this high resolution regional model. Now, I'm not saying that it's a dynamic or statistical model right now. Spoiler alert, it's dynamic because I'm here at this workshop as well. But you could, in theory, use a statistical model, right, to model things of air temperature change or precipitation change, right? There's a whole bunch of statistical downscaling techniques out there. But really the question is, how do you build a useful model? And for things like fish habitat, river ice, you really need to think about headwater catchment scale modeling. And that's kind of this, for the atmospheric folks, meso beta, even maybe meso gamma, so 10 kilometers on a side. And so you think you need a model grid spacing that's less than that, right? I mean, we're not quite to 4 or 8 delta X of a 10 kilometer box, but we're getting there. So we're kind of thinking of, you go from the coarser resolution to this 4 kilometer resolution on the right, you can start to see all of the detail of these catchments that influence seasonality of stream flow, what subsequent river temperatures would be, how the river ice is going to evolve. I'm not going to talk about that. We're just trying to build the kind of the climate model here. There's other folks that are working on those pieces. So really it's all about orographics here. There's not a lot of convection, right? So really all of the benefit comes from resolving orography for the atmosphere and the land, right? So you can think about orographic precipitation, spatial patterns of temperature and precipitation, right? So temperature decreases as your elevation increases typically. And so if you can actually resolve your high peaks, you're doing a better job immediately, in theory. And so we're using this RASM model that Mark introduced, which is great. So this is the Regional Arctic System model. We're actually kind of the ones that are leading this change from VIC to CTSM, which for folks who don't know CTSM, it's the rebranding of CLM, so the NCAR Community Land Model. It's now the Community Terrestrial Systems Model. There's some things that are happening as far as software engineering and capabilities that garnered a new acronym. But the main reason for us to do this is that VIC isn't quite as complex as we might want from a process perspective. And so some of the things you would want to model for change, you might think you want a better process representation here. And so then, we're working with the RASM team to feed this back to the model development branch. So the idea here is this co-production is also giving us cool science. That's kind of one of the points I want to advertise, is we're able to do model development work even though we're kind of an applied science team. So our specific configuration is a land atmosphere only. Our expertise lies there. We don't really have ocean expertise, so we prescribe the ocean and the sea ice. These are kind of just RASM specific. So 4 kilometer horizontal resolution, this is our domain with some river basins highlighted. That the next talk, Yifan's going to talk about detailed evaluation of the hydrology. And so one of the things that folks have been talking about so far is, this idea of tuning or optimization. So we're doing that here as well. I just thought I would maybe try to motivate it a little bit, is like the idea of doing all this is like, we want a model with limited biases, right? Because we have trust in the model then, but also like from a impact standpoint, you don't want to do bias correction if you don't have to, because it does potentially breaks things that you wouldn't necessarily want to break, like variable covariance, right? How does precipitation and temperature covary? How does precipitation, temperature, and radiation covary? You might think the dynamical model would do a better job. Also, most of the statistical downscaling schemes don't necessarily downscale all the variables you would want. So we are also tuning or optimizing our models. We're kind of doing it in an approach where we're actually adding in formal land model optimization. So we have the capability in RASM to run the land model offline. So we're actually doing, Yifan will talk about this, a formal. So by formal, I mean like we define an objective function and we run the model hundreds to thousands of times, and we actually find an optimum, right, a global or semi-global minimum in the objective function. And then we also, at the same time, we're doing this kind of subjective expert tuning of the atmosphere using kind of a default CTSM. And then we go back and we combine it all together, retune as needed. We actually had even though you might think land-atmosphere coupling isn't that strong here for as compared to like the Great Plains, we actually in our formal optimization, right, it doesn't care about physical realism. So we had a situation where, and this goes back to Martin's talk, the hydrology was great, but the Bowen ratio was terrible, and so we were pumping so much moisture into the atmosphere, we just generated a bunch of low clouds, and our temperature and precipitation simulation was terrible. So we actually had to go back and fully re-optimize the land model with different parameter bounds, and then rerun the coupled system. And so just an example of all the things that have to happen to even just make a regional application work. And so I'm not going to, how much time do I have? 2 minutes, perfect. So I'm not going to spend a lot of time on this slide because there's more that I want to talk about from the co-production, co-design. But this is all to say that after we do all of this offline optimization with the land model, go back to the fully coupled model and run it for close to 20 years, our performance is holding, which is great. It may even slightly improve. So this is just some skill score for a bunch of these river basins that I showed. And this is the coupled skill score, and this is the offline skill score. And you can see if you bounce across basins, it's generally holding. It's worse on the north slope. And really, what do you do with skill scores like this? How do you assess the fit for purpose? So Yifan's going to talk more about that. And so where we're going with this then is, projection simulation. So this historical simulation that the previous one slide was referring to is almost done. It's a 30-year run over this time period for us with ERA 5. Then we'll also be performing 2 kind of PGW simulations using CMIP6 models. We're developing those now, the forcing data. And then we have a large pot of compute to do 4 direct ESM downscaled simulation sets, so the 30-year reference, 30-year mid-century. And this is all motivated by this survey that we also did. So taking advantage of social scientists on the team and other things is we developed a full survey to go out to these different decision-making bodies. And this is just an example question of what types of extreme events you might be concerned about, and those are the different answers that we got. And so you can take kind of information like this and try and blend it into how you would develop future scenarios. Not too shocking, there wasn't really a consensus on events or concerns except for the near-term future. And this is something that we also hear from Western agencies like the National Park Service or the USGS or any agency that might be, maybe not the USGS, but the National Park Service, other Forest Service, anybody that's managing Army Corps of Engineers, reclamation, anybody that's into management. You need to manage the next 30 years to get to the end of the century. So when we show all these pretty results, which are cool about science of the end of the century changes, well, we still need to get there. And so the managers really want to know what is the next 30 years, which is difficult from a projection standpoint too, because you have to then worry a little bit about, well, what is the initial state of the global model? Is it in a PDO, positive to negative phase, et cetera? And so we're trying to develop these PGW scenarios and then direct ESM downscaling using kind of information about features of interest. And then I'll just stop here just to say, I don't think I appreciated how much work co-development, co-production was. It's also very worthwhile. And I think it's still, and this is, I'll take it right out of the NCAR strategic plan, the buzzword of actionable climate science. I think this is actually a nice example of how to maybe do it where you still get to do cool science and you still get to do model development work. And I'll stop there.
Thank you. Question? Maybe I will ask one. So this morning, Martin Bess said that we need like this hill, slope, flow, and everything when we go to high resolution. Yep. But do I understand it correctly that CTSM already has everything in?
So we have hill slope. We have a representation of hill slope hydrology, which is definitely critical. There is surface water retention, so things like, the kind of the concept of the prairie pothole or the Arctic potholes is in here. Some of the pie in the sky two-way coupling is not, right? So like CTSM doesn't yet have full two-way coupling with the channel and the groundwater and the surface water. We also don't have stream temperature, so that's offline modeling. There are projects starting or soon to be starting at NCAR, and we're trying to develop external funding to do those things within CTSM. So some of it's there. You know, it's kind of like, I personally think the important processes are there, but probably not fully.
Quick question.
Yeah, hi Andy. Thanks for sharing that perspective. And I think, you know, this cross-cultural work, as you shared, is extremely hard. I was reading a book by Hans Rosling, who was a medical guy who did international health, and he's famous for his bubble diagrams of economics and health metrics. But he was just saying, you know, what he learned in all of his work in various parts of the world is that you can send a survey out and you'll get responses, but it doesn't really tell you the story. And I was kind of thinking about that little, you know, what are the important things to you thing. And first of all, there weren't, like the number of responses weren't real large.
No.
But you know, his point is you actually have to go sit down and talk to these folks to really learn what's really important. And it isn't just give them a questionnaire. You sit down and say, you know, how do your kids get to school in the morning?
Yep.
And how long does that take? And, oh, you know, the boat can't cross the river, the current's too hard. Then you learn things like that.
Yep.
So
yep.
I don't know if that's...
So I didn't show it here, but the response rate for that survey was like 10%, which is pretty terrible objectively for a survey. So the IAC, our Indigenous Advisory Council, we have monthly meetings with them. So those are a virtual sit down, and they represent a lot of the different communities. So that's part of what helps having the Yukon River Intertribal Watershed Council on our research team. We get their science advisor, science director's input at all of our meetings and, you know, in emails and everything all the time. Some of our social scientists, like Nicole Herman Mercer at the USGS, she's worked in Alaska for over a decade, close to 2 decades, and so she has institutional knowledge of communities. She does field work up there regularly. Some of the USGS people are in Alaska. They're at the Alaska Science Center. And so we are trying to be as plugged in as possible. We also have a field component and community observation components, right? All of these things that it takes to build these relationships. I'm glad you made that comment, because like relationships is really where it is. The surveys are mildly useful at best, but it's part of the process. You want to try and get as much information as you can.
Thanks, Andy.
Let us move to the next talk. Thank you. So the next talk is by Yefan Cheng, still about Alaska.
So this is the last talk about Alaska. Hi, I'm Yifan Chen. I'm currently a project scientist here at NCAR, and today I'm going to follow up with Andy's talk, and mainly talk about like the novel application, the high-resolution application, and multi-objective optimization of the community terrestrial system model, which was the community land model by here at NCAR. And okay, so next slide. So this is part of the National Science Foundation Navigating the New Arctic project. And we work closely with indigenous Alaskans to investigate the climate impacts on the Alaskan and Yukon rivers, fish, and communities. And the Arctic is rapidly changing, such as the large increases in temperature and precipitation, and decreases in sea ice and changes in seasonal snowpack. And climate change also heavily impacts the freshwater systems in Alaska, which the indigenous Alaskans heavily rely on them for subsistence fishing, as well as transportation. And the rapidly changing Arctic hydrology is influenced by complicated land surface processes. Some example could be the increasing active layer depths of the permafrost greatly influence the subsurface runoff process. The strong surface energy fluxes lead to early snow melting, frozen soil warming, which also changes the stream flow seasonality. And in this study, we are trying to use a state-of-the-science land model, the community terrestrial system model, for a regional application, and we are trying to move CTSM towards a more actionable earth science paradigm through optimization for hydrology-related applications. So we configured a high-resolution study, CTSM application, which is 4 kilometers in this study. So we have over 200,000 grid cells in our study domain. So it is very, given the considerations for computational costs, we select 4 representative river basins for optimization, including from north to south is Kuparuk, Beaver, Salcha, and Toktina. And we conduct a multi-objective optimization for river flow and snow. And for the time's sake, I will not go in detail about the objective functions. So what we do here is we try to synthesize the community efforts in the Earth system modeling and trying to develop an optimization workflow for CTSM. So for the upper box here, which is, shows how we configure high-resolution high-resolution baseline scenario for CTSM, we downscale the meteorological forcing data of from ERA5. We update the soil texture and organic matter using the high-resolution soil grade data sets. And we also take advantage of the hill slope hydrology, which is built in CTSM by Sean Swanson at NCAR to account for the subgrade variability. And for the optimization workflow, the first 2 steps is trying to select sensitive parameters for Arctic hydrology. The third the third step is doing optimization using a method called adaptive surrogate-based optimization, which is developed by Duan, and he is in Hehai University in China. And the last step is the parameter regionalization. And I want to highlight that the optimization model framework developed in this study can be easily transferable to other CTSM regional applications because we use some data sets which is globally available. And I want to highlight the perturbed parameter ensemble experiment, which refers to as PPE, which is parameter sensitivity and a global parameter sensitivity analysis. And we can use this experiment to select sensitive CTSM parameters, not only to hydrology variables, but also to hundreds of other variables. So some results. The first results is we do an evaluation of the optimized parameters, and we do this using the 30-year time series, because when you do optimization, you only optimize for 5 years. And our result shows the flow simulations improves at 13 out of 15 river basins based on the Klein-Gupta efficiency for daily flow. And the mean Klein-Gupta efficiency increases from 0.43 to 0.63 after optimization, and the mean Nash-Sutcliffe efficiency increases from 0.09 to 0.45 after optimization. And I want to draw your attention to this large river basin, which is the Yukon River at Pilot Station, which has a confluence area of 824,000 square kilometers. And its KGE increases from negative 0.36 to 0.7, and so which to some extent proves our optimization is highly efficient, because the confluence area we used for optimization only occupies 3% of the confluence area for this station. So we also evaluate the snow simulation using the satellite-derived Geographic Information Network of Alaska, which is short for GINA, and we specifically look at 3 metrics, including the first snow date, FSD, the last snow date, LSD, and the snow duration. So basically, the default and optimized snow simulations shows very similar performance and spatial patterns. which, for example, they both have an earlier first snow date and a later last snow date, and therefore a prolonged snow duration. But the optimized snow simulation shows a slightly smaller biases than the baseline simulation. So the definition of actionable science actually suggests that we need to have a benchmark that a model has to hit before we can use the model results to inform decision making. So first, we select one metric called Nash cycle efficiency, because this is a metric that is used by the water management authorities in the United States. And we select two additional metrics, including the percent bias in the flow duration curve, the high segment volume, which to evaluate the bias in the high flow. And for the low, because our indigenous advisory council and the climate information survey shows that they are generally interested in the flooding. And also we look at the biases in the summer low flow, because the summer low flow has very strong impact on the the juvenile salmon's production rate. And for those two metrics, the high flow bias and low flow bias, there's no like universally accepted benchmarks. So we use the baseline as our benchmark. So in general, our optimization improves the overall and high flow. So for the overall flow, 9 out of 15 meet the benchmark after optimization, and only 2 meet the benchmark before optimization. For a high flow metric, 13 out of 15 basins have improved high flow after optimization. But we can see that there is a dry bias in the low flows. So the percent bias in the summer low flows decreases from negative 100.08 to negative 136%. And only 7 basins show better performance in capturing low flow events. So we also conducted a climate sensitivity analysis to assess whether CTSM captures the response of flow simulations to the changes in precipitation and air temperature. So the black dots denotes observations, the blue dots denotes uncalibrated scenarios, and the orange dot denotes optimized scenarios. The subplots here are organized based on the confluence area, with the smallest on the top left and the largest on the bottom right. So when optimization improves the sensitivity to precipitation change, we mark P on the top right corner, and similarly to air temperature, we mark T on the top right corner. So basically, you can see for the 8 largest river basins in our study domain, at least one climate sensitivity was improved after optimization. And in 4 of the large river basins, both climate sensitivities improves. But you can see for the smaller river basins, the climate sensitivity actually did not get improvement or even get slightly worse. Oh, what I'm doing? Oh, sorry. So the last result slides. So we are curious we perturbed 14 different parameters, and we are curious the contributions of each optimized parameters for the flow performance improvement in our study. So we use a technique called the Shapley decompositions. So basically, we find half of the 14 parameters in our study in the land model is not directly related with hydrology. They are actually related with vegetation and sensible or latent heat fluxes. And we find the perturbation of the 7 non-hydrological parameters contributes to a total of 56% 5 to the KG improvement in the northern part of the region and contributes 15.5 of the KG improvement in the southern part of the region. And the different parameter contributions across regions reflects that the spatial heterogeneity of parameter sensitivities to Arctic hydrology. So takeaway, Alaska is one of the most challenging regions in hydrological modeling because it's complicated land surface processes. So in general, our optimization framework improved the general hydrological simulations in Alaska, which including the better overall and high flow simulations, and also limited improvement in the snow simulations and slightly worse low flow simulation and mixed improvement in the climate sensitivity. But it still has its potential for use-inspired applications across the rest of the world. That's my talk. Thanks.
Thank you. Thank you. There is time for one question. Okay, maybe this will reflect my... Masaki.
Yeah, thank you very much. I learned a lot. But one question is, do you have any observation to validate your process? I think that such a kind of hydrological land process is important. Do you have a detailed observation basis for?
What kind of processes?
Yeah, melting of land or something.
So when we are doing the optimization, we using the streamflow data from USGS. And for the snow, we use snow tail sites up in Alaska. They are both observation data. Like in the when we are optimize the parameters.
Okay. Mm-hmm. So you developed the new. You are using the existing land model.
Yes.
Right. Okay. Thank you.
Yeah, I'm not like developing any new process or parameterization inside CTSM. I'm using the existing CTSM model.
Thank you. Thank you very much.
Yeah, thanks.
Let's move to the next talk by Timothy Schneider. We stay on the hydrology.
So I think I've violated every principle of building presentations that I've learned over many years of doing this. But there's a method to the madness. I realize we're going to be leaving these slides with you, so they're dense. There's a lot of information in them. I got way more than I can really speak to a lot, so I'm going to move through fairly fast, but the idea is the information's there for you to refer to. So I'm going to talk about what I think is a very exciting opportunity we're trying to create to do the kind of science we're talking about here in this workshop about regional hydroclimate projects. Where do I point to make it go? Oh, I'm going backwards. It helps to go forwards. So at the end of the day, I hope that maybe I've convinced you this regional hydroclimate project idea is a good way to do a lot of the science we're talking about here. And so just loosely running through the agenda, we'll talk about what an RHP is, why we need one, a little bit about the one we're proposing, and then kind of an invitation and a timeline, next steps. The link here is the science plan for GWEX. You know, it has a collection of goals and science questions. We're sort of adhering to those. I just didn't have the time to talk about them, so I put the link there. And I love this line from this poem, Among School Children by W.B. Yeats, that goes, you know, how can we know the dance from the dance? And the more I think about this in the context of the science we do, the more layered it becomes. But for some reason that got linked to this in my mind, and it seems like that's what we're trying to do, is we're trying to understand the dance and the dancers and how they make the dance. But there's a lot more to it. We'll have beer. So a little bit about what RHPs are. RHPs are a construct out of GWEX. GWEX, for those who don't know, is part of the World Climate Research Program. It's one of the 4, I believe, core projects. And within GWEX, there's these panels that kind of exercise the work, and GHP, the GWEX Hydroclimatology Panel, is where these RHP projects happen. And basically, they're these large, regionally focused, multidisciplinary projects. And really, we're just trying to understand the weather, climate, and hydrology and the processes in that region. So you see on the map here that there are many of these around the world. There's some going on. There's many that have happened in the past and are done. There's some being prepared, and there's some that are aspirational. And the one here in the United States is one of those aspirational, you can see circled in orange, one of these ones that have been desired for more than a decade now. There's been many attempts. This is at least the third attempt to get this thing off the ground, and like a fool, I volunteered. So the way we're couching this regional hydroclimate project for the U.S. is as a 10-year effort to understand and characterize the water, energy, and carbon cycles in the Anthropocene, of course, over the U.S. It's being driven by a need to produce actionable information, products, tools, etc., in collaboration with the stakeholders to address climate justice. That's a big issue. Climate doesn't affect us all equally. And water, food, and energy security, and in this sense, energy is now like the energy we produce and use and consume for both natural and human systems. Tall order. The figure on the bottom is just kind of encapsulating the idea, right? As you look back in time, the uncertainty gets bigger. As you look forward in time, can we beat down the uncertainty and what we understand happened in the past to use as a basis for understanding what may happen in the future? Why do we need one? Part two, you know, it's no sane or reasonable person can argue the point that humans are the dominant force in changing the planet Earth in virtually every way possible. We probably, somewhere about now, have hit 8 billion people, and we have a massive impact. Here's just, you know, a couple looks at one metric. Here in the U.S., how much water we use per capita. One metric is withdrawals, what we're pulling out of the system, amounts to about 1,200 cubic meters per year per person. Or if you want to look at sort of water use per capita, right, it ends up being like 2,200 gallons per day. That's an enormous impact just on the water system alone. By the way, this article in the New York Times by actually one of the members of our group, Andrew Schwartz, who runs the Berkeley Central Sierra Snow Lab, wrote this really nice article about what's keeping him up at night about drought in California. Another look at why do we need an RHP. There's a science case we can make, right? We know it's a very complex coupled system. Energy and water and carbon cycles are all linked through various terms. Evapotranspiration being prominent among them. That's a tricky little beast to get a handle on. So it's very difficult. And in spite of GAP and GSIP, which were the previous iterations of these RHPs here in the U.S., more than a decade ago, we still have a long ways to go before we can actually close the water and energy budgets in the U.S. And there's this nice paper, and I know someone kind of pinged me about this, right? It was a paper by Jessica Lundquist in 2019 in BAMS, where she made the argument that, at least for mountain hydrology, our ability to model the system is now starting to outstrip our ability to observe and measure it. So this was a bit of a clarion call for, you know, we need to do better on the observations. We're modeling at finer scales, we're representing more processes. We need more observations, better observations, more kinds of observations. So we need to act as a community. I'm not going to go too much into this, but you can also make sort of a programmatic case, you know, about effective use of taxpayer dollars, leveraging what we have, being more efficient and more effective. And we're partnering, and at the end of the day, somehow, if we're going to do this, we need support, and these are the people with the dollars. So we need to work with them to make this happen and to help them meet their agency missions. So the scope. So the map represents our notion of what the geographic scope of this ought to be. There's lots we could unpack in here. You'll see there's some blobs on the map. The idea behind the blobs is to illustrate, and don't take them literally, please, that they may end up being close to what happens, but they're not intended to suggest this is what has to happen. But they're observational transects, and this could be leveraging existing observational infrastructure. For example, we have the ARMCART site in Oklahoma. The U.S. Geological Survey is implementing what they call the Next Generation water observing system. They're working in the Delaware, so I threw a couple blobs up there. The SAIL campaign, also from DOE, is happening in Upper Colorado right now. NOAA has assets in the hydrometeorology test bed, or at least they used to when I ran it. I think they still do. So anyways, we can leverage these, but we should complement them. And there's an idea coming out of the GWEX community called the GLAFO, the GWEX Land Atmosphere Feedback Observatory, and our colleague Volker Wolfmeyer and his folks in Germany have built one of these things in Germany, a LAFO. So can we leverage new things like that, which is really aimed at measuring the energy exchanges in 3 dimensions, 4 dimensions, from below the surface through the boundary layer at least. So that's the geographic scope, and this is, I think, where we want to support with the modeling. I do want to say one quick other point about this, and just an acknowledgement. So today we're all here on the lands of the Arapaho, Cheyenne, and Ute people. They've been here for tens of thousands of years. They're still here. They're going to be here for a long time. And that place-based knowledge and wisdom is tens of thousands of years old. And so there's, and Andy kind of teed me up a little bit here with his work in Alaska that he shared, but there's a lot we can learn from them, and by working together we can leverage our traditions. So the last comment about the scope here is this figure, and Peter and Martin best shared this and talked through this slide, kind of this evolution of our representation at the land. So I don't need to belabor it. Peter suggested I use this, but the notion is, I think this RHP, if we anchor it with this regional modeling here over the United States, but we also have global models, and there's information there, and they can do different things and answer different questions. We can do regional modeling at this scale at 4 kilometers now for 40 plus years. Took 11 months on the USGS supercomputer, and we used a quarter of it, but we did it. But the global models can go for hundreds of years. They're coarser, and of course these very fine processes like watershed scale type stuff happen as well. And what does this enable? Just one quick little cool result, I think, of the kinds of things we can do. This is again another mountain one, but if we define the Upper Colorado above Lee's Ferry, right, that's the source of water for 40 million people in the southwestern U.S. It accounts for irrigates about 5 million acres of cropland, and it estimates that it's about $1 trillion of economic activity it supports annually in the U.S. It's an important thing, and it's way oversubscribed. Most of the time, the water never even makes it to the ocean. And the stream flows are declining. So this paper here by Chris Milley and Krista Dunn in the USGS came out in 2020. It's a really nice paper, but they looked at the sensitivity, the change in, I got to really move, the change in runoff as a function of the change in warming, right? And what they found in their analysis is it's about 9% decrease in runoff in the Upper Colorado Basin for every degree of warming they're seeing. But then they looked at an RCP 8.5 and found that in the future, depending on what happens with precip in the basin, it could either be a 3% increase in runoff down to a 40% decrease, which would be beyond catastrophic. This is an example of the CONUS 404 I mentioned earlier. It's 40-year, 4-kilometer simulation. It's actually 42 years. This is just a snapshot, but you can see the detail here as this anchor for this modeling, which we can then do much finer at the hill slope scales and much coarser, but maybe longer terms at the global. We're going to organize our plan into these themes. This came out of our affinity group, which has been running for a little over a year now. So just to be very brief, there's a social science component, a mountain hydrology, land atmosphere, impactful extremes, organized convection and precipitating systems, and then this advanced observational systems. We identified so far working group leads for 4 of these. We're working on pinning down the last couple. We're going to write a science plan. Before I get to that, though, so we envision having some kind of hub, test bed, whatever you want to call it, that will support this. And so there's this halo of activities that it will support, but then the hub will provide the governance and the places where people can get data and models and code and blah, 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 and we can all work together and be one big happy family. Maybe even sing Kumbaya, who knows. But then you might speculate, right, given the advent now of this digital Earth lighthouse activity, that perhaps this hub is actually really just a digital twin or digital Earth regionally, right? And the idea then is this becomes the place where we can turn data, it's about the knowledge value chain, right? We can turn data into information, information into knowledge, knowledge into wisdom. So that's the link that we're proposing here back to the WCRP Digital Earth Lighthouse activity. Timeline, just briefly, we hope to have a first draft, fairly light, but a science plan that we'll present to the GHP. If they approve, we become an initiating RHP. We then have a formal recognition within the GWEX community, and that will help us with our federal partners who are interested in this and they're engaged. Last thing I'll say, this is the last one, is it's an invitation to come play with us, come join us. There's a link if you want to sign up. We got 142 people. You can see a list of talks, way more than that we've had, but we're shifting now into actually developing some plans. And I hope once we get a plan in place, we can start playing with like Dakota's 404 data and Ruby Lung's data with the E3SM and all kinds of other stuff. So again, these are all here for reference. Thank you.
Thank you. So we have time for one question.
That was a whirlwind.
Is there a reason why it is only focusing over the US?
Pardon me?
Is there a reason why your RHP are only over the US?
Yes, it's because each region has its own. I'll try to get back to this quickly. It's almost there. It's because there are already RHPs happening. There's one in Canada that's it's in its last year or two called Global Water Futures. There's a very successful one in the Baltic called Baltic Earth. There's one spinning up in South America. So yeah, there are many happening, and actually that's an advantage of this, right? Is the international community is doing similar things, and by being a part of this GWEX group, you know, we can all learn from each other, and it brings cross-cutting projects across these, like TMEX, for example, to the table as well. So.
Okay.
I hope folks join us.
Thanks for the advertisement. So we go to the last talk of this afternoon. We go to the hot climate again, so the RFR. Our last speaker is Ari Prasad Dasari.
Thank you very much. I think this is only one talk which is about the hot. I think this is only one talk about the Middle East region, which is very hot region. So here I want to present some of our results. Subseasonal predictability of the rainfall over the Kingdom of Saudi Arabia. Even though we have very small amount of rainfall, even if you count the number of days or the total amount, but it is very important because the soil infiltration is very low. And this is the major objective of this one is improve forecast capability at subseasonal to seasonal time scales for the convective extremes in the Kingdom of Saudi Arabia using regional climate model and convective parametric modeling. And these results are published in most recently in the Climate Dynamics. So what we did here, so the workflow, we took ECM WF subseasonal reforecast and we downscale to using the RCM for the S2S time scale. Then we generated like 20 winter seasons, 20 years of the winter seasons. And again, we reforecast using our CPM. But we don't have data to validate these results. So what we did, parallelly we developed a regional reanalysis for that region at 5 kilometer resolution by focusing with Iran interim reanalysis. And also we collected some of the observations for that region and we assimilated into that one. And then we are using that one as a proxy to validate these results. Of course, we parallelly validated that one with the multiple observations and also we published multiple papers on the last section. Now I want to present the results of this on the red colored one. So this is the region where we designed our domain, and the domain is the resolution is 4 kilometers, and we gave like every week we used to start forecast and we go forward up to 4 weeks, and then we have like 20 years of month-long forecast, but each one starts at every week and between November to April. So we have so much of data we generated. And then we picked it. I told that where we are using this data, the reanalysis data. So if you see the mean patterns of the 42 years of the rainfall over the Arabian Peninsula, mainly I am talking about the Kingdom of Saudi Arabia. The rainfall actually associated with winter, November, December, January, February, March, and April. But the most of the rainfall, if you see, they are in the summer month, but they are in the southern Red Sea region. The narrow one is Red Sea, and southern one, which is mostly associated with this monsoon, Indian summer monsoon system. So these are the spatial patterns of the mean picture of the rainfall over that region. And when we talk about this, the predictability of these ECMWF reforecast and also after downscaling, whatever we got this one. And these are the mean patterns for the week 1, week 2, week 3, week 4. And the corresponding, if you see the reanalysis, this one is the particular one. This is total accumulated rainfall for that week. And the biases, if you see that the top one is about the ECM forecast, and this one is our forecast using forced with the ECMWF. The bias is actually reduced over the land region when compared to the ECM's forecast. So that is actually added value what we gained from this one. And this is about 30 to 40% of the rainfall. And this is actually much more, improvement we saw on the land region. But there is the oceanic region, if you see, mainly on the southern Red Sea region, we have the large positive biases. So what we did it here, this is one of the relative operating characteristics curve, which usually is used to assess the ensemble forecast. So from 0 to, if you plot the diagonal between this corner to that corner, if something is, the curve is towards the northeast sector, then your predictive model or performance is better. If it is down, it is not performing well. So all these ensembles, if you see, there is a big improvement between, compared to ECMWF with the WARP. And then what we did actually, we counted the area of these curve which below this ROC, and we projected for this the whole week's forecast for the first 1 week lead time, say 2 weeks lead time, 3 weeks lead time, and 4 week lead time. In all these things, the blue ones are the multiple ensembles from the WARP, and the red ones are the ECMWF. So there is an improvement between these two things. But interestingly, what we saw from the March 27th, roughly last 2 weeks or 3 weeks, we didn't saw much difference. Added value between the convective parameterization scheme or this ECMWF. So we digged inside, so what is happening? So we took that reanalysis data. We collected all the number of rainy days over the entire region. We applied the storm analysis, self-organized map analysis. And then we identified that rainfall over this region is associated with 3 types of large-scale items. One is with the extratropical influence, and because of the patterns, especially the upper level trough and the Red Sea trough and the anticyclone, Arabian anticyclone of that region. And if you have that type of alignment, that's mostly associated with the extratropical influence. And the bottom one is mostly with the tropical influence, and the third one is the transition one. So based on this one, we separated the days which are associated with the C1, C2, C3. And then we projected that one. So where we gained by using the CPM. So we gained more the added value, the rainfall events which are associated with the extratropical mode. And the tropical mode we gained a little bit, but not compared to the extratropical mode. We don't have the other one, but it is in between these two. So almost like, I will say, we gained like 0.796 compared to 0.653, which is almost like, I will say, 20 to 30% larger, added value for the extratropical mode, and here it is around 5 to 10%. So this is the summary of my talk. And the summary of, this is very clear that the subseasonal for this Arabian Peninsula region, the CPMs are added value in prediction of the dry precipitation. compared to the raw ECMW of STS reforecast. So I will stop this one, but I have one slide. And most recently, this is just 1 week ago, we got funding to start the Climate Change Center at the university and funded by the Ministry of Environment. And we have officially started inaugurated last week. And here we have 3 objectives. Objective 1 is sub-seasonal to seasonal scale forecast for the Arabian Peninsula region. And the second one is the climate change projections, regional climate change projections, I would say. And the third one is what are the mechanisms are associated with these the extremes or whatever. And we have multiple collaborators. Already we have, contract agreements between many institutes. And along with that one, we are also developing the database and also the tools to visualize or tools to data distribution. And also, we are going to use this one for decision-making tools and all. And we have a big supercomputer in our university, and next year it is going to be upgraded almost 6 times faster than this one. Thank you very much. Yeah.
Thank you very much. There is time for questions. Christian?
Yeah, I may have missed that, but did you downscale the entire ensemble? So you take the ECMWF ensemble,
Forecast, yeah.
the entire S2S ensemble, so I don't remember how many members. 11 members. That's quite a lot of computation, actually, at 4 kilometers.
Too big.
Any further question? No? Thanks again.
Thank you very much.
Well, so the last for the day, Tim.
So I was thinking a little bit, right? I remember a long time ago, a colleague told me there was a paper that said the initial conditions can impact your simulations for up to 100 days. And I tried to track that paper down. I never did find it, but I'm just curious when you start going to these, finer resolutions and then you start pushing them out to such long time periods, do you see any impact then of the effect of doing fine resolution at very long time periods? I mean, you showed some improvement in skill, right? So that suggests things are going well, but it's just a partially formed question in my head. I'm not even sure if it's making sense, but.
Yeah, I didn't mention that. I mean, it's not simply, forward run. So we use spectral imaging to constrain the boundaries. So in that way, we're actually managing the balance between the large scale and the small scale features.
Thank you.
Okay, so thanks, and let's thank all the speakers of this afternoon session. And we will meet again tomorrow at 9, I guess. Have a nice evening, dinner, and see you tomorrow.